Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's first oceans and the quiet emergence of life within their ancient depths. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, the Earth breathed steam into a sky that knows no blue. Water exists everywhere and nowhere, suspended as vapor in an atmosphere so thick with heat that no drop can fall, no ocean can form. The planet's surface glows cherry red beneath crushing clouds. A world where water waits in the space between states, neither liquid nor entirely gas, but something altogether more patient. The sun burns 25% dimmer than it will in our time, yet the Earth radiates its own warmth from within, heated by the constant percussion of asteroids and the slow decay of radioactive elements deep in its molten heart. Steam rises and condenses and rises again in endless cycles, never quite achieving the weight necessary to fall. The atmosphere holds water like a meditation on possibility, each molecule suspended in thermal currents that spiral upward from the molten surface like invisible rivers flowing toward space. In this primordial greenhouse, atmospheric pressure reaches levels that would crush any familiar form of life. Perhaps 100 times denser than the air we breathe today, carbon dioxide and water vapor dominate this ancient sky, creating a blanket so effective at trapping heat that surface temperatures soar beyond the boiling point of water at sea level, yet water persists, held aloft by thermal currents that never cease, creating a planetary sauna where vapor and liquid exist in constant, restless exchange. The Earth spins faster in these early days, completing a full rotation in perhaps 14 hours rather than 24. This rapid spin drives fierce atmospheric circulation patterns, creating planetary-scale hurricanes of superheated vapor that rage for centuries without pause. These storms dwarf anything in the modern world, circulation systems larger than continents, sustained by the planet's internal heat and the relentless bombardment from space. Lightning crackles continuously through the dense atmosphere, not the brief flashes familiar to modern storms, but sustained electrical discharges that illuminate the steam-wrapped world for hours at a time. Methane drifts through this ancient air, released from volcanic outgassing and the breakdown of carbon-rich materials delivered by comets and asteroids. Hydrogen escapes constantly to space, bleeding away from the planet's gravitational grip because the atmosphere burns too hot to hold these lightest of elements. Ammonia compounds cycle through the vapor, creating brief moments of alkalinity in an otherwise acidic sky. The chemical complexity of this early atmosphere rivals that of the most exotic laboratory experiments, yet it persists naturally across an entire world for millions of years. Gradually, imperceptibly, the bombardment lessens. Fewer rocky visitors arrive from the outer reaches of the solar system, and the Earth begins its long exhale. The late heavy bombardment winds down like a cosmic engine running out of fuel, leaving longer and longer intervals between the massive impacts that once punctured the forming crust and sent plumes of vaporized rock spiraling into space. Temperature drops not in sudden plunges but across geological epochs, degree by degree, until somewhere around 4 billion years ago, a threshold crosses that science still struggles to precisely define. The mystery lies in exactly when and how this transition occurred, whether gradually across millions of years or in relatively rapid pulses that transformed the entire planet's surface. Some evidence suggests the cooling happened in fits and starts, with massive volcanic events occasionally reheating the atmosphere just as it approached the critical temperature for water condensation. Other clues point toward a more steady decline, like a planetary fever slowly breaking across deep time. The truth likely encompasses both patterns, creating a complex dance between cooling and reheating that stretched across epochs. Impact events during this period released energy equivalent to billions of nuclear weapons, instantly vaporizing any surface water and launching molten rock into ballistic trajectories that painted the sky with incandescent trails. Yet between these catastrophic interruptions, the planet attempted again and again to cool, like a patient learning to walk who falls and rises and falls again. Each cooling period lasted longer than the previous one. Each heating episode grew less severe, until finally the intervals of stability stretched long enough for water to persist on the surface. Zircon crystals, some of the oldest minerals preserved on Earth, whisper contradictory stories about this period. These tiny grains, smaller than sand particles but harder than steel, formed in the cooling magma of the earliest crust. Chemical signatures trapped within their crystalline structure suggest that liquid water might have existed briefly on the surface much earlier than previously thought. Perhaps as early as 4.5 billion years ago, the oxygen isotope ratios within these ancient zircons indicate interaction with liquid water at temperatures far cooler than the molten hellscape that supposedly characterized the Hadean Earth. But these same crystals also bear the scars of repeated melting and recrystallization, evidence that any early water was likely vaporized again by subsequent impacts and volcanic events. They preserve within their atomic structure the memory of multiple heating and cooling cycles, like geological hard drives storing the planet's traumatic infancy. Some zircons show evidence of having formed in the presence of evolved igneous rocks, granites and rhyolites that require extensive chemical differentiation to produce, suggesting that even in the Hadean, the Earth's crust was developing complexity far beyond simple basaltic flows. Only took 40 million years or so for the first stable oceans to form, only required the patience of an entire planet cooling, only needed every water molecule in the atmosphere to finally surrender to gravity's gentle insistence. The irony rests in how the most dramatic transformation in Earth's history, the birth of its seas, occurred with such profound stillness that no witness could have perceived the change within a single lifetime. What appears instantaneous in geological terms actually unfolded across time spans longer than the entire history of complex life on Earth. When the first droplets finally fall, they strike basalt so hot that they instantly return to steam, like whispers against a furnace. But persistence defines this process more than drama, and eventually the surface cools enough that water remains water, pooling in the countless depressions left by impact craters and volcanic collapse. The earliest rains fall not as gentle showers, but as torrential downpours that continue for thousands of years, drawing down the vast reservoir of atmospheric water vapor grain by grain. Drop by drop, these primordial storms reshape the planet's surface through pure erosion, carving channels and valleys in the fresh volcanic rock, creating the first river systems that flow toward the growing pools of collected water. The sound of this endless rain echoes across a world without life to hear it, a percussion symphony performed for stone and steam alone. Each raindrop carries dissolved gases from the atmosphere, slowly altering the chemistry of the surface as acid rain etches new minerals from volcanic glass and basalt. These first seas stretch shallow and warm across continents that barely exist, covering a world that resembles no place familiar to modern eyes. The ocean floors consist almost entirely of dark volcanic rock, unweathered and sharp-edged, creating a landscape as alien as any distant planet. No beaches exist yet. No gentle transitions between land and sea, just the hard boundary where basaltic flows meet the growing water. The contrast appears absolute: black rock, clear water, steam-hazed sky. The water itself carries none of the familiar chemistry of modern oceans, fresh and nearly pure. It lacks the dissolved salts and minerals that will later define marine chemistry. These primordial seas taste of rain and volcanic gases, slightly acidic from dissolved carbon dioxide and sulfur compounds, but otherwise clean in a way that no natural water on Earth will ever be again. Like planetary tears collecting in stone basins, the first oceans hold within their depths the potential for everything that follows. Vast laboratories where chemistry will gradually discover life. The transformation from vapor to liquid occurs not as a single moment, but as a slow continental sigh that stretches across millennia. Atmospheric temperatures hover at the knife's edge between states, where water molecules dance between gas and liquid with the delicacy of a planetary breath. Steam condenses on particles of volcanic dust suspended in the dense air, each grain serving as a nucleus around which the first droplets can form. These condensation nuclei, microscopic fragments of silicate minerals and sulfur compounds, drift through the superheated atmosphere like seeds of possibility. Without them, pure water vapor would remain suspended far beyond its normal condensation point, a phenomenon scientists call supersaturation. The atmosphere becomes a vast cloud chamber where phase transitions happen slowly, molecule by molecule, as if the planet itself learns the physics of precipitation through trial and error. Volcanic ash provides the most abundant condensation sites, with each eruption launching billions of tiny particles into the stratosphere. These silicate fragments, some no larger than viruses, carry electric charges that attract water molecules through electromagnetic forces. Iron-rich particles prove especially effective at nucleating droplets, their metallic surfaces providing the molecular scaffolding around which water can organize itself from chaos into structure. Sulfur dioxide from volcanic outgassing creates aerosol particles that serve similar functions, though these dissolve into the forming droplets and acidify them with compounds that will later play crucial roles in weathering reactions. Temperature gradients develop in the thick atmosphere as heat radiates away to space while the surface continues to glow with residual warmth. These thermal layers create zones where water vapor can finally achieve the density necessary for gravitational collapse. The first droplets form not near the surface, where temperatures remain too extreme, but in the cooler reaches of the upper atmosphere, miles above the molten ground. Here, at altitudes where atmospheric pressure drops to levels that allow water molecules to slow their frantic thermal motion, the first tentative coalescence begins. The physics of droplet formation under these extreme conditions follows rules that no longer apply anywhere on the modern Earth. Pressure-temperature relationships exist in regimes that scientists can only approximate in laboratory diamond anvil cells or computer simulations. Water behaves differently under such conditions. Its surface tension, viscosity, and thermal conductivity all shift in ways that affect how droplets grow, merge, and eventually become heavy enough to fall. Convection currents in the dense atmosphere create vertical circulation patterns that carry water vapor upward into these cooler zones with tremendous efficiency. These ascending columns of steam rise like invisible thermal elevators, powered by the heat differential between the glowing surface and the cold vacuum of space above. As vapor ascends, it expands and cools adiabatically, following thermodynamic laws that govern how gases behave when pressure decreases. This cooling provides the energy gradient necessary for phase transition, converting the kinetic energy of molecular motion into the potential energy of liquid cohesion. Scientific uncertainty surrounds the precise mechanics of this transition. Computer models struggle to replicate the complex interactions between atmospheric chemistry, thermal dynamics, and the planet's rapidly evolving surface conditions. The equations governing fluid dynamics become nonlinear under these extreme conditions, creating mathematical chaos that makes long-term predictions nearly impossible. Some simulations suggest that water condensation occurred in discrete pulses, triggered by massive volcanic eruptions that temporarily cooled the atmosphere with reflective particles. Other models indicate a more gradual process, with steam slowly accumulating into larger and larger droplets over geological timescales. The problem of modeling early Earth's atmosphere resembles trying to predict weather patterns in a hurricane while simultaneously calculating the physics of boiling water, both familiar processes that become intractably complex when combined at planetary scales. Modern atmospheric models require simplifying assumptions that may not hold true for the extreme conditions of the Hadean Earth. Temperature variations of even a few degrees could shift the entire system between stable states, making the boundary between steam and rain as sensitive as a chemical equilibrium balanced on the edge of a phase diagram. Only took a few million years for gravity to finally win its patient argument with molecular motion. Only required the perfect balance between atmospheric pressure, temperature, and the availability of condensation sites. Only needed every water molecule to surrender its kinetic energy to the planet's inexorable pull. The irony lies in how this fundamental physical process, the simple transition from gas to liquid, becomes one of the most difficult periods in Earth's history for scientists to understand or replicate in laboratory conditions. The earliest precipitation falls as droplets far larger than modern raindrops, formed in the dense atmosphere under pressure conditions that no longer exist on Earth's surface. These proto-raindrops plummet through the thick air like liquid bullets, accelerating to velocities that would shatter on impact with solid rock. The terminal velocity of falling water changes dramatically in such dense atmosphere. Droplets can grow to sizes that would be impossible in modern air, sustained by the thick medium through which they fall. Yet the surface they strike remains soft with heat, semi-molten basalt that hisses and steams as water contacts stone. The impact creates miniature explosions of vapor, each droplet instantly returning to the gaseous state but carrying with it dissolved minerals and thermal energy. These micro-explosions carve tiny craters in the cooling rock, creating surface textures unlike anything seen in the modern world. The constant bombardment of water droplets begins the planet's first erosion processes. Mechanical weathering on a scale so minute that millions of impacts are required to remove even microscopic amounts of material. Each raindrop carries within its molecular structure a record of the atmospheric chemistry through which it fell. Dissolved carbon dioxide creates weak carbonic acid that begins the planet's first weathering reactions. The concentration of CO2 in these early droplets far exceeds modern levels, creating water with a pH comparable to weak vinegar. Sulfur compounds from volcanic outgassing add their sharp chemical signatures to the mix, introducing sulfuric acid components that further enhance the chemical reactivity of the falling water. Trace metals vaporized from asteroid impacts season these primordial waters with elements that will later prove essential for life: iron, nickel, cobalt, and others suspended in solutions more dilute than the faintest tea. Gold and platinum group elements, delivered by impacting meteorites and then volatilized by the heat of impact, circulate through the atmosphere and condense into droplets that rain precious metals onto the cooling surface. These early oceans contain dissolved concentrations of rare elements that will never again be matched in Earth's history. The sound of this endless precipitation echoes differently in the dense atmosphere, creating resonances and harmonics impossible in modern air. Sound waves propagate through the thick medium with frequencies and amplitudes that would be deafening to any hypothetical listener. Rain falls not with the familiar patter against leaves and earth, but with the deep percussion of liquid striking molten rock, accompanied by the constant hiss of steam rising back toward the clouds. This audio landscape plays continuously for thousands of years, a planetary symphony performed without audience, creating the acoustic backdrop for Earth's transition from fire to water. As droplets strike the cooling surface and instantly return to vapor, they carry with them dissolved minerals leached from the contact with hot basalt. This water vapor, now chemically enriched, rises back into the atmosphere where it will condense again, fall again, and repeat the cycle with each iteration, slightly altering both the atmospheric and surface chemistry. These countless repetitions create the planet's first biogeochemical cycles, primitive versions of the complex elemental circulation that will later support living systems. The mystery deepens when considering that this steam-rain-steam cycle must have continued for geological ages before any water could remain stable on the surface. Each molecule of water might have completed thousands or millions of these cycles, gradually cooling the surface through the constant exchange of latent heat, slowly building toward the moment when liquid could finally persist in permanent pools. The total energy involved in this phase transition equals the thermal output of millions of volcanoes, all of it derived from the gradual cooling of an entire planet and slowly released through the patient physics of evaporation and condensation. The first pools form in the deepest craters, where asteroid impacts have excavated basins below the general level of the cooling crust. These impact scars, some hundreds of kilometers across, create natural catchments that collect the earliest persistent water. Gravity draws the sparse precipitation toward these low points, beginning the slow accumulation that will eventually become Earth's first stable bodies of standing water. Each crater tells a story written in shocked minerals and melted rock. The violence of formation creates unique geological signatures, quartz grains transformed into high-pressure polymorphs that exist nowhere else in nature. Feldspar crystals shattered into microscopic fragments by shock waves traveling faster than sound. An impact glass cooled so rapidly that its atomic structure remains frozen in disorder. These mineral transformations occur only under the extreme conditions of hypervelocity impact, creating rock types that serve as permanent records of the cosmic bombardment that shaped early Earth. The largest impact basins, those created by asteroids tens of kilometers in diameter, excavate cavities that penetrate deep into the planet's crust. These megacraters expose layers of rock that formed during the earliest stages of crustal solidification, bringing to the surface mineral assemblages that reveal the chemical composition of the primitive mantle. The excavated material forms rim structures that rise kilometers above the surrounding terrain, creating mountainous barriers that influence local weather patterns and water retention for millions of years after the initial impact. Shock metamorphism in these impact sites creates new mineral phases that dissolve more readily in water than their unshocked equivalents. Mascalinite, a shocked form of feldspar, releases sodium and aluminum ions into solution at rates far exceeding those of normal plagioclasa. Diaplectic glass, formed when quartz is compressed beyond its elastic limit, dissolves silica into the early pools at concentrations that approach saturation. These enhanced dissolution rates create the first natural examples of accelerated chemical weathering, processes that will later become crucial for maintaining the chemical balance of mature oceans. The water that collects in these craters remains hot enough to dissolve minerals at rates far exceeding modern weathering. Basaltic rock, still cooling from the heat of impact, releases sodium, calcium, magnesium, and iron into solution at concentrations that turn the early pools into natural mineral broths. The chemistry resembles that of extremely hot springs, but on a scale encompassing entire lake systems. Steam rises constantly from these thermal pools, creating localized weather patterns that cycle water vapor between the growing lakes and the overlying atmosphere. Hydrothermal circulation develops spontaneously in the deeper crater lakes as water heated by contact with hot rock rises through convection while cooler surface water descends to replace it. These circulation cells transport dissolved minerals throughout the water column, creating vertical chemical gradients that vary with depth and temperature. The hottest waters near the bottom of these crater lakes reach temperatures approaching the boiling point even under the increased atmospheric pressure of the early Earth, creating conditions similar to those found in modern submarine hydrothermal vents. Temperature differences between the heated crater floors and the cooler surrounding terrain drive convection currents that begin to connect isolated pools. Water vapor rises from the warm basins, condenses in the cooler air above the crater rims, and falls as precipitation on the surrounding landscape. This precipitation flows back toward the craters as the first primitive drainage systems, carving channels through volcanic ash and loose debris. Gradually, these channels grow deeper and more defined, creating the earliest river networks that link separate water bodies into connected systems. The development of these early drainage networks follows patterns determined by the chaotic topography left by impact bombardment and volcanic activity. Unlike modern river systems that evolve gradually through headward erosion and stream capture, these primitive waterways often form catastrophically when temporary dams of volcanic debris fail and release impounded water in massive floods. These flood events carve channels tens of meters deep in a matter of days, creating permanent pathways that guide subsequent water flow for geological ages. Impact-generated fracture systems provide additional pathways for water movement both on the surface and underground. The shock waves from large impacts create radial and concentric fracture patterns that extend for hundreds of kilometers beyond the crater rim. These fractures serve as preferential pathways for groundwater flow, creating subsurface connections between apparently isolated surface pools. Springs emerge along these fracture networks, bringing heated groundwater to the surface and creating oases of persistent water even in areas not directly supplied by surface precipitation. The mystery of how these isolated pools eventually merged into continuous ocean basins remains one of the fundamental questions about early Earth's hydrology. Computer models suggest that the process required not just the accumulation of precipitation, but also significant tectonic activity that lowered some areas while raising others. The early crust, still hot and relatively plastic, responded to the weight of accumulated water by subsiding, creating positive feedback loops where the presence of water encouraged further water retention. Isostatic adjustment, the sinking of the crust under the weight of accumulated water, occurs much more rapidly during this period than it would on the modern Earth. The hot, plastic nature of the early crust allows it to deform readily under load, creating basin subsidence rates measured in centimeters per year rather than the millimeters per millennium typical of modern geological processes. This rapid subsidence creates accommodation space for water accumulation at rates that match or exceed the rate of precipitation input, ensuring that the early oceans can grow continuously rather than overflowing their basins. Scientific uncertainty surrounds the timeline of this merging process. Some evidence from ancient zircon crystals suggests that connected ocean basins formed relatively quickly, within a few million years of the first stable pools. Chemical signatures preserved in these early minerals indicate interaction with large bodies of water rather than isolated pools, suggesting rapid development of extensive water coverage. Other geological indicators point toward a much more gradual process, with isolated lake systems persisting for tens of millions of years before eventually overflowing their crater boundaries and joining together. The debate centers partly on the question of whether early Earth experienced one or multiple episodes of ocean formation. Some scientists propose that the first oceans formed and were subsequently vaporized by large impacts, requiring the entire process to repeat multiple times before stable water coverage could persist. Others argue for a more linear progression from isolated pools to connected basins to global oceans, with each stage building incrementally on the previous one without major setbacks. Only took gravity and time to convince separated waters to find each other. Only required the patient excavation of connecting channels through volcanic debris and cooling lava flows. Only needed the simple physics of overflow to link crater lake to crater lake across an entire planet. The irony rests in how the most violent events in Earth's history, Asteroid impacts that released more energy than all human nuclear weapons combined created the gentle basins where water first learned to rest. Volcanic activity during this period contributes as much to basin formation as asteroid impacts. The cooling crust develops weak points where magma can break through to the surface, creating volcanic vents that both destroy existing topography and build new landforms. Some eruptions excavate calderas larger than modern cities, creating instant lake beds that fill with water as soon as they cool enough to prevent immediate evaporation. The Yellowstone caldera, one of the largest on modern Earth, would appear modest compared to some of the volcanic collapse structures that formed during this early period. Other volcanic events build shield volcanoes and cinder cones that alter drainage patterns and redirect the flow of accumulating water. These volcanic constructs serve as natural dams, impounding water in areas that would otherwise drain towards lower elevations. The rapid construction of volcanic barriers can create lakes overnight, trapping water that then begins its own local cycles of evaporation, precipitation, and chemical weathering. When these volcanic dams eventually fail through erosion or renewed volcanic activity, they release stored water in catastrophic floods that reshape vast areas of the early landscape. The interaction between volcanism and hydrology creates feedback mechanisms that shape the planet's early surface. Water accelerates the cooling of lava flows, causing them to solidify into barriers that redirect subsequent water flow. The cooling effect can create flow-front barriers, where advancing lava meets standing water, causing the molten rock to pile up rather than spread laterally. These barriers alter local topography in ways that persist long after the volcanic activity ceases, creating permanent features that influence drainage patterns for millions of years. Steam explosions occur when water contacts hot volcanic rock, creating phreatomagmatic eruptions that excavate new basins while simultaneously launching water vapor back into the atmosphere. These steam blasts redistribute both water and rock debris across wide areas, homogenizing the early landscape and creating the relatively flat terrain necessary for extensive shallow seas. The explosions also fragment volcanic rock into fine particles that dissolve more readily in water, accelerating chemical weathering processes. Pillow lavas form when volcanic eruptions occur underwater, creating bulbous, rounded rock structures that provide evidence for the presence of liquid water during specific volcanic episodes. These pillow structures preserve within their glassy rinds the chemical signatures of the water in which they formed, providing geochemical clues about the composition and temperature of the early oceans. The discovery of ancient pillow lavas in some of Earth's oldest rock formations confirms that substantial bodies of liquid water existed much earlier than previously thought. Tidal forces from the nearby moon play a larger role in early ocean dynamics than they will in later periods. The moon orbits much closer to Earth during this time, perhaps only 15 to 20,000 kilometers away compared to the current distance of nearly 400,000 kilometers. This proximity creates tidal bulges in the early oceans that rise and fall by hundreds of meters rather than the few meters familiar to modern coastlines. These extreme tides pump enormous amounts of energy into the early ocean basins, driving circulation patterns and mixing processes that accelerate chemical weathering and mineral dissolution. The gravitational interaction between Earth and the nearby moon also affects the planet's rotation and the length of its days. Tidal friction gradually slows Earth's spin, while simultaneously pushing the moon into a more distant orbit through conservation of angular momentum. During the period when the first oceans form, days last perhaps 8 to 10 hours, creating rapid day-night cycles that drive thermal expansion and contraction in the surface rocks. These temperature fluctuations contribute to mechanical weathering processes that break rocks into smaller fragments, increasing the surface area available for chemical reactions with the accumulating water. Chemical gradients develop in the growing water bodies as different minerals dissolve at different rates and under different temperature conditions. Iron-rich basalts release ferrous ions that give the early oceans a distinctive greenish tint, while the dissolution of sulfur-bearing minerals creates local zones of acidic water that can dissolve even resistant minerals like quartz. Calcium and magnesium concentrations build up in areas where feldspar-rich rocks undergo intensive weathering, creating chemical microenvironments that will later influence where the first biological processes can take hold. As isolated pools overflow and connect, they create the planet's first major rivers. These early river systems flow not through soil and vegetation, but across bare volcanic rock, carving channels with the persistence of liquid water acting on stone. The rivers carry dissolved minerals from the highlands toward the growing ocean basins, beginning the chemical transport processes that will eventually establish the salinity gradients and elemental distributions characteristic of mature seawater. The earliest rivers flow intermittently, surging during periods of heavy precipitation and drying to mere trickles during atmospheric lulls. But their channels preserve the pathways that will guide water flow for geological ages. The merger of crater lakes into continuous water bodies transforms the planet's albedo, its ability to reflect solar radiation back to space. Dark volcanic rock absorbs solar energy efficiently, but water surfaces reflect a larger portion of incoming sunlight, especially when covered with the reflective steam that rises from the still, warm early oceans. This change in albedo creates a cooling feedback mechanism that accelerates the condensation of atmospheric water vapor, speeding the transition from a steam-dominated to a water-dominated world. The growing seas begin to taste of stone and time as minerals dissolve into water for the first time in planetary history. Sodium leaches from cooling feldspar crystals at rates measured in geological moments, each grain surrendering atoms that have remained locked in crystal lattices since the first crustal solidification. The dissolution occurs grain by grain, molecule by molecule, as weakly acidic water penetrates microscopic fractures and attacks the chemical bonds that hold silicate minerals together. Weathering reactions proceed according to temperature-dependent kinetics that operate far faster in the early Earth's warm environment than they will in any subsequent period. The elevated temperatures of both water and rock create conditions where chemical equilibrium shifts dramatically toward dissolution, allowing even resistant minerals to contribute their elements to the growing chemical complexity of the early oceans. Albite feldspar releases sodium and aluminum, while anorthite contributes calcium and more aluminum, beginning the slow construction of seawater's ionic inventory. Basaltic glass dissolves most readily, its disordered atomic structure offering numerous attack points for hydrolysis reactions. The volcanic glass contains trapped gases and volatile elements that bubble out as the solid matrix breaks down, releasing carbon dioxide, sulfur dioxide, and trace gases into the overlying water. These dissolved gases alter the pH of the early seas, creating local zones of acidity that accelerate weathering while simultaneously neutralizing themselves through reaction with basic minerals in the surrounding rock. Iron oxidation begins as soon as ferrous minerals contact the early atmosphere's trace oxygen content. Though oxygen remains scarce in these early times, enough exists to slowly convert metallic iron and iron-bearing silicates into iron oxides that dissolve readily in the warm, slightly acidic water. The dissolved iron gives the early oceans their distinctive coloration, a greenish hue that reflects the unique chemistry of a world where metals flow freely through aqueous solution without biological interference. Scientific uncertainty surrounds the exact sequence of chemical processes that establish the early ocean's composition. Laboratory experiments can replicate individual weathering reactions, but the complex feedback loops between atmospheric chemistry, water temperature, and mineral dissolution rates prove difficult to model accurately over geological timescales. The rate at which different elements entered solution depends not only on their mineral sources, but also on their chemical behavior once dissolved. creating a complex web of interactions that determines which elements accumulate and which precipitate back out of solution. The mystery deepens when considering that some elements essential for later biological processes appear in the early oceans at concentrations far exceeding those found in modern seawater. Dissolved iron concentrations may have reached levels thousands of times higher than current oceanic values, while trace metals like copper, zinc, and molybdenum circulated freely through the water column. These high metal concentrations reflect the absence of biological processes that would later remove these elements from solution through incorporation into living tissues. Only took a few million years for every major rock-forming mineral to contribute something to the growing chemical library of seawater. Only required the patient action of water on stone to begin the redistribution of elements that had been locked away since planetary accretion. Only needed time and temperature to convince atoms that had formed in stellar cores to dissolve and flow through liquid solutions for the first time since their creation. The irony lies in how this fundamental process of chemical weathering, so familiar from modern environments, operated under conditions so extreme that its products bore little resemblance to any natural water found on Earth today. Evaporation from the warm ocean surfaces begins to concentrate dissolved materials in ways that create the first natural examples of chemical precipitation. As water vapor rises into the atmosphere, it leaves behind its dissolved cargo, gradually increasing the concentration of ions in the remaining liquid. When these concentrations exceed saturation limits, mineral precipitation occurs, creating the first sedimentary deposits on the ocean floors. Halite crystals form in shallow evaporative basins where solar heating drives water loss faster than precipitation can dilute the accumulating salts. These early salt deposits differ from modern evaporates in their chemical composition, reflecting the unique elemental ratios of the primitive oceans. Iron-bearing salts precipitate alongside sodium chloride, creating mineral assemblages that preserve chemical signatures of the early atmosphere and hydrosphere within their crystal structures. Calcium carbonate precipitation begins as soon as dissolved calcium concentrations reach supersaturation levels in the presence of carbonate ions. The carbon dioxide content of the early atmosphere ensures abundant carbonate availability, but the precipitation kinetics depend strongly on temperature, pH, and the presence of nucleation sites. Small calcium carbonate crystals begin forming in the water column itself, creating mineral snow that settles slowly through the warm ocean depths. The chemical gradients that develop within these early seas create distinct water masses with different properties at different depths and locations. Surface waters, heated by solar radiation and direct contact with the atmosphere, maintain the highest temperatures and the most active evaporation rates. These surface waters concentrate dissolved salts while simultaneously losing volatile compounds back to the atmosphere through outgassing processes. Deeper waters remain cooler and denser, creating stable stratification that limits vertical mixing and allows chemical gradients to persist for long periods. The deepest waters contact the still warm ocean floor, where they undergo hydrothermal reactions that add different suites of dissolved elements to their chemical inventory. Manganese, chromium, and other transition metals enter solution preferentially in these deep, hot environments, creating chemical signatures that distinguish bottom waters from surface waters. Hydrothermal circulation cells develop in areas where ocean water contacts particularly hot crust, creating the first submarine hot springs. These early hydrothermal systems operate at temperatures and pressures that exceed those found in most modern submarine vents, generating chemical environments where unusual mineral reactions can occur. Serpentinization reactions transform olivine-rich rocks into serpentine minerals while producing hydrogen gas and methane, beginning the planet's first examples of chemosynthetic energy production. The sulfur chemistry of these early hydrothermal systems differs dramatically from modern analogues due to the different atmospheric composition and dissolved gas content of the primitive oceans. Hydrogen sulfide concentrations reach levels that would be toxic to any modern life forms, while sulfate availability remains limited by the scarcity of atmospheric oxygen needed for sulfur oxidation reactions. These chemical conditions create reducing environments where metals remain dissolved at concentrations impossible in modern oxidizing oceans. Trace element patterns in the early seas reflect the random nature of early crustal composition combined with the non-selective dissolution processes operating under high-temperature conditions, elements that will later become essential for biological processes, such as phosphorus, nitrogen compounds, and various transition metals, circulate through the early oceans at concentrations determined purely by their abundance in the source rocks and their chemical behavior in aqueous solution. The phosphorus cycle begins as apatite minerals in igneous rocks slowly dissolve, releasing phosphate ions into the water column. Unlike in modern oceans where biological processes rapidly remove dissolved phosphate from solution, the early seas allow phosphorus concentrations to build up over time. This phosphorus accumulation creates one of the chemical prerequisites for the later evolution of energy-storing molecules that will become fundamental to life. Nitrogen chemistry in the early oceans reflects the limited availability of molecular nitrogen from the atmosphere and the absence of biological nitrogen fixation processes. Most nitrogen circulates as ammonia and simple nitrogen-bearing organic compounds delivered by comets and asteroids. These reduced nitrogen species remain stable in the low-oxygen environment of the early seas, providing a reservoir of nitrogen compounds that will later become crucial for protein synthesis. Silica dissolution from volcanic glass and crystalline silicates creates supersaturated solutions that begin precipitating amorphous silica deposits on the ocean floors. These early silica precipitates differ from modern biological silica in their purely inorganic origin and their trace element chemistry, which reflects the diverse metal content of the dissolving source rocks. The precipitation process removes silica from solution while concentrating other dissolved elements, contributing to the ongoing chemical evolution of seawater composition. In the deepest reaches of the early ocean basins, where water meets the cooling but still molten edges of the planetary crust, the first hydrothermal vents begin their patient work of chemical transformation. These underwater hot springs emerge not as discrete point sources, but as diffuse zones of heated water seepage, where seawater penetrates fractured rock and returns to the ocean floor, carrying dissolved minerals that will reshape the chemistry of the entire water column. The temperature gradients around these early vents exceed anything found in modern hydrothermal systems. Water temperatures approach 400 degrees Celsius near the discharge points, maintained in liquid state only by the immense pressure of the overlying water column and the elevated atmospheric pressure of the early Earth. At these temperatures, water becomes a powerful solvent capable of dissolving minerals that remain stable under normal surface conditions, creating chemical cocktails of unprecedented complexity. Fractured basalt provides the pathway for this hydrothermal circulation as seawater percolates downward through networks of cooling cracks in the newly formed ocean floor. The descending water heats gradually as it approaches the molten rock below, undergoing progressive chemical changes as it reacts with the hot minerals it encounters. Olivine transforms to serpentine through hydration reactions that consume water molecules while releasing hydrogen gas and heat, creating a positive feedback loop that sustains the circulation system. The chemistry of these early hydrothermal systems operates under reducing conditions that favor the formation of organic compounds from simple inorganic precursors. Carbon dioxide dissolved in the circulating seawater reacts with hydrogen gas produced by serpentinization reactions, creating methane, formaldehyde, and more complex carbon-bearing molecules through Fischer-Tropsch type synthesis reactions. These abiotic organic synthesis pathways operate efficiently under the high temperature, high pressure conditions found in the deep circulation zones. Scientific understanding of these early hydrothermal processes relies heavily on laboratory experiments that attempt to replicate the extreme conditions of the Hadean ocean floor. High pressure, high temperature apparatus can reproduce some aspects of the early vent chemistry, but the complex interaction between flowing water, reactive minerals, and organic synthesis reactions proves difficult to study comprehensively. Computer models struggle with the nonlinear chemical kinetics that govern these systems, particularly when multiple reactions occur simultaneously under rapidly changing temperature and pressure conditions. The mystery of exactly how these early hydrothermal systems contributed to the origin of life remains one of the most active areas of research in early Earth science. The chemical environment of the early vents provides many of the molecular building blocks needed for biological processes. But the pathway from simple organic molecules to self-replicating systems remains unclear. Some researchers propose that mineral surfaces in the vent systems served as catalysts for more complex organic synthesis, while others suggest that the thermal gradients themselves provided the energy needed to drive uphill chemical reactions. Only took a few million years for these underwater laboratories to begin producing the molecular inventory that would later become essential for living systems. Only required the marriage of water and hot rock to create conditions where carbon chemistry could explore possibilities beyond simple oxidation and reduction. Only needed the patient circulation of heated seawater through fractured basalt to begin the planet's first examples of complex organic synthesis. The irony rests in how these violent, high-energy environments created the gentle chemical conditions necessary for life's eventual emergence. Metal sulfide precipitation occurs where hot, metal-rich vent fluids encounter the cooler, sulfide-bearing seawater of the early oceans. The temperature differential triggers rapid precipitation of pyrite, pyrrhotite, and chalcopyrite, creating mineral chimneys that grow upward from the vent discharge points. These sulfide structures differ from modern black smoker chimneys in their chemical composition and growth rates, reflecting the unique metal concentrations and sulfur chemistry of the primitive oceans. The growing sulfide chimneys create their own microenvironments where temperature, pH, and chemical composition vary dramatically over distances measured in centimeters. These chemical gradients provide numerous distinct reaction zones where different types of organic synthesis can occur simultaneously. Amino acid formation occurs in moderate temperature zones where ammonia reacts with organic acids, while more complex polymerization reactions take place in higher temperature regions where thermal energy can drive the formation of longer molecular chains. Iron-sulfur minerals precipitating in these vent systems possess catalytic properties that promote organic chemistry reactions impossible in simple aqueous solution. Pyrite and pyrrhotite surfaces provide reaction sites where carbon monoxide and hydrogen can combine to form organic compounds through pathways similar to those used in industrial chemical synthesis. These mineral-catalyzed reactions operate efficiently under the reducing conditions of the early vents, producing organic molecules that would require complex biochemical pathways to synthesize in modern environments. Serpentinization reactions in the deeper parts of the hydrothermal circulation systems produce alkaline fluids with pH values exceeding 11, creating some of the most chemically reactive environments on the early Earth. These highly basic solutions can dissolve silica from surrounding rocks while simultaneously precipitating carbonate minerals from dissolved carbon dioxide. The alkaline conditions also favor the formation of complex organic molecules from simple precursors, particularly reactions that build larger molecules from smaller ones through condensation reactions. The interaction between alkaline vent fluids and the more acidic early seawater creates precipitation zones, where pH gradients drive complex chemical reactions. These reaction fronts move slowly through the water column as the different chemical solutions mix, creating dynamic environments where the chemical conditions change continuously. Some researchers propose that these moving chemical gradients could have provided the energy gradients necessary to drive the formation of the first metabolic networks. Thermal gradients around the vent systems create convection currents that transport dissolved chemicals throughout the local water column. Hot, mineral-rich fluids rise from the vents while cooler seawater descends to replace them, creating circulation cells that efficiently mix the various chemical components produced by the hydrothermal reactions. This circulation ensures that organic molecules synthesized in the high-temperature vent zones are transported to cooler regions where they can persist without thermal decomposition. The chemical diversity produced by early hydrothermal systems exceeds that found in any modern natural environment. Hundreds of different organic compounds form through the various synthesis pathways operating under different temperature and pressure conditions throughout the vent systems. Simple molecules like methane and hydrogen cyanide combine to form amino acids, while aldehydes and organic acids polymerize into longer chains that resemble the building blocks of modern biomolecules. Mineral precipitation in the cooler zones surrounding the vents creates layered deposits that preserve chemical signatures of the early hydrothermal activity. These deposits contain organic molecules trapped within their crystal structures, creating a geological record of the types of chemistry that operated in the early vent systems. Analysis of these ancient deposits provides direct evidence for the abiotic synthesis of complex organic compounds under early Earth conditions. The energy budget of early hydrothermal systems far exceeds that of modern analogues due to the higher heat flow from the still cooling planet and the greater temperature differentials between the hot crust and the overlying seawater. This abundant energy drives chemical reactions at rates much faster than those observed in modern hydrothermal environments, allowing complex organic synthesis to occur on timescales relevant to geological processes rather than requiring the extended reaction times typical of low-energy systems. Clay mineral formation occurs in the intermediate temperature zones of the hydrothermal systems as aluminum-bearing solutions react with silica-rich fluids. These early clays possess unique chemical properties due to their formation under the extreme conditions of the early vents, including unusual trace element compositions and surface reactivities. Some researchers propose that these clay minerals served as primitive catalysts for organic synthesis reactions, providing surfaces where simple molecules could concentrate and react to form more complex compounds. The sulfur isotope signatures of minerals precipitating in early hydrothermal systems differ significantly from those found in modern vents, reflecting the different atmospheric composition and sulfur cycling processes of the early Earth. These isotopic signatures provide clues about the temperature conditions and chemical pathways operating in the ancient vents, allowing scientists to reconstruct the chemistry of these systems from minerals preserved in ancient rock formations. Complex organic molecules begin forming spontaneously in the mineral-rich waters around underwater volcanic systems, following chemical pathways that operate according to thermodynamic principles rather than biological design. Carbon monoxide dissolved in the hydrothermal fluids reacts with hydrogen gas produced by serpentinization reactions, creating formaldehyde and methanol through reactions that proceed efficiently under the reducing conditions of the early vents. These simple organic compounds serve as building blocks for more complex molecular architectures that will later become essential for life. The Fischer-Tropsch synthesis pathway operates naturally in the early hydrothermal environments, converting carbon dioxide and hydrogen into organic compounds through reactions catalyzed by iron-sulfur mineral surfaces. This abiotic process produces a diverse mixture of organic molecules, including fatty acids, alcohols, and simple hydrocarbons that form spontaneously under the high temperature. High-pressure conditions found in the deep circulation zones. The molecular products of these reactions accumulate in the cooler waters surrounding the vents, creating chemical environments enriched in organic compounds. Amino acid synthesis occurs through multiple independent pathways in the early vent systems. The Strecker synthesis converts aldehydes, ammonia, and hydrogen cyanide into amino acids through reactions that proceed readily under hydrothermal conditions. Simultaneously, reductive amination pathways convert organic acids and ammonia into amino acids using hydrogen gas as a reducing agent. These parallel synthesis routes ensure abundant production of amino acids, the molecular building blocks that will later become essential for protein formation. Nucleotide precursors form through reactions involving phosphate minerals dissolved from apatite-bearing rocks in the hydrothermal circulation systems. Ribose and other simple sugars form through formose reactions that convert formaldehyde into more complex carbohydrates under alkaline conditions. Nucleotide bases arise from the polymerization of hydrogen cyanide in the presence of ammonia, creating purines and pyrimidines through pathways that operate efficiently in the chemical environment of the early vents. The mystery of how these diverse organic molecules became organized into the first self-replicating systems remains one of the central questions in origin of life research. Laboratory experiments demonstrate that individual synthesis pathways can produce the molecular components needed for life. But the transition from chemical diversity to organized metabolism proves more difficult to understand. Some researchers propose that mineral surfaces served as organizing templates that concentrated and aligned organic molecules in ways that promoted more complex chemistry. Scientific uncertainty surrounds the question of whether early organic synthesis occurred primarily in high-temperature vent environments or in cooler, more stable chemical systems. High-temperature synthesis proceeds rapidly and produces diverse molecular products. But many organic compounds decompose at the elevated temperatures found near active vents. Cooler synthesis environments may preserve organic molecules more effectively, but produce them more slowly, creating a trade-off between synthesis rate and molecular stability. Only took a few 100,000 years for the random chemistry of hot water and rock to begin producing molecules that would later serve as the foundation for all biological processes. Only required the patient exploration of chemical possibility space under conditions where thermodynamics favored organic synthesis over decomposition. Only needed the marriage of carbon chemistry with mineral catalysis to begin creating molecular complexity beyond anything found in simple aqueous solution. The irony lies in how these chaotic, high-energy environments produce the organized molecular structures that would later become the hallmark of living systems. Fatty acid formation occurs through the reduction of carbon dioxide in the presence of iron-sulfur minerals and hydrogen gas, creating long-chain organic molecules that possess amphiphilic properties essential for membrane formation. These early fatty acids differ from their biological counterparts in their branched structures and unusual chain lengths, reflecting their abiotic origin and the unique chemical conditions under which they form. The fatty acids accumulate in the cooler waters around the vents, where they begin spontaneous self-assembly into primitive membrane structures. Polymerization reactions create longer molecular chains from simple organic precursors through condensation reactions that eliminate water molecules while forming new chemical bonds. Thermal energy from the hydrothermal systems drives these uphill reactions that would not proceed spontaneously under normal conditions, allowing the formation of primitive proteins from amino acids and simple nucleic acids from nucleotide precursors. The polymerization occurs most efficiently at intermediate temperatures, where thermal energy promotes bond formation without causing rapid decomposition. Catalytic properties of iron-sulfur minerals accelerate organic synthesis reactions by providing surface sites where reactant molecules can concentrate and interact. Pyrite and pyrrhotite surfaces possess electron transfer properties that facilitate reduction reactions, converting carbon dioxide and other oxidized carbon compounds into organic molecules through pathways that parallel modern biochemical processes. These mineral catalysts operate continuously without depletion, providing sustained organic synthesis capability throughout the lifetime of the hydrothermal systems. Organic molecule concentrations in the early vent systems reach levels far exceeding those found in modern natural environments. Amino acid concentrations may exceed millimolar levels in the immediate vicinity of active vents, while fatty acid and simple carbohydrate concentrations achieve similar levels in the cooler zones where these molecules remain stable. These high concentrations create conditions where intermolecular interactions and polymerization reactions can occur at rates relevant to geological timescales. Chiral selection begins to emerge in some organic synthesis pathways as mineral surface catalysis favors the formation of specific molecular conformations over their mirror images. Quartz surfaces and certain clay minerals exhibit preferential binding for one enantiomer over another, creating slight but persistent asymmetries in the organic molecules produced through mineral catalyzed synthesis. These early examples of chirality selection may have provided the foundation for the homochirality that characterizes biological molecules. Chemical gradients around the hydrothermal vents create distinct reaction zones where different types of organic synthesis occur simultaneously. High-temperature zones near the vent outlets favor the formation of simple organic compounds through rapid thermochemical reactions, while intermediate temperature zones promote polymerization and more complex molecular assembly. Cool zones at the edges of the hydrothermal plumes allow for the preservation and further organization of the organic molecules produced in the hotter regions. The carbon isotope signatures of organic molecules synthesized in early hydrothermal systems reflect the abiotic pathways through which they form, providing geochemical fingerprints that distinguish them from organic compounds produced by biological processes. These isotopic signatures preserve evidence of early organic synthesis in ancient rock formations, allowing scientists to identify locations where complex chemistry operated on the early Earth even when the organic molecules themselves have been destroyed by subsequent geological processes. Sulfur-bearing organic compounds form through unique pathways available only under the reducing conditions of the early hydrothermal systems. Thiols, disulfides, and other sulfur-organic molecules arise through reactions between organic precursors and hydrogen sulfide dissolved in the vent fluids. These sulfur-bearing compounds possess chemical properties that make them particularly effective at forming complex molecular structures and participating in electron transfer reactions that will later become essential for metabolism. Self-replicating ribonucleic acid molecules appear in the chemical soup of the early oceans through processes that transform random molecular interactions into organized information storage and transfer systems. RNA emerges not as a single moment of creation, but as the gradual organization of nucleotide building blocks into chains capable of storing information in their sequence while simultaneously catalyzing their own reproduction. This dual capacity for information storage and catalytic activity makes RNA uniquely suited to bridge the gap between lifeless chemistry and living systems. The assembly of RNA from its component nucleotides follows thermodynamic principles that favor polymerization under specific conditions of temperature, pH, and ionic strength found in the early hydrothermal environments. Ribose sugars, phosphate groups, and nucleotide bases combine through phosphodiester bond formation, creating the backbone structure that will later become universal among all living organisms. The polymerization occurs most efficiently on mineral surfaces that concentrate the reactants and provide catalytic sites for bond formation. Clay minerals, particularly montmorillonite and other layered silicates, serve as natural templates for RNA polymerization by providing ordered surfaces where nucleotides can align and react. The spacing between clay layers matches the dimensions of nucleotide molecules, creating geometric constraints that favor the formation of properly structured RNA chains. These mineral templates also protect forming RNA molecules from hydrolysis reactions that would otherwise break down the phosphodiester bonds as quickly as they form. Random sequence RNA molecules exhibit varying degrees of catalytic activity, with some sequences proving capable of catalyzing their own replication, while others remain chemically inert. This variation in catalytic ability creates the first examples of molecular selection, where RNA sequences that can replicate themselves become more abundant than those that cannot. The selection process operates purely through chemical kinetics, without any external guidance or biological machinery. The mystery of how the first replicating RNA molecules achieved sufficient fidelity to maintain stable genetic information remains one of the central puzzles in origin of life research. High-fidelity replication requires complex molecular machinery that does not yet exist, while low-fidelity replication produces so many errors that genetic information cannot be preserved across generations. Some researchers propose that early replication systems operated with intermediate fidelity levels that allowed gradual improvement through evolutionary processes. Scientific uncertainty surrounds the question of whether RNA emerged in a single location and spread throughout the early oceans, or arose independently in multiple hydrothermal systems simultaneously. Evidence from laboratory experiments suggests that RNA formation requires very specific chemical conditions that might have existed only in limited environments, while theoretical models indicate that successful replicating systems could spread rapidly once established. The truth likely involves elements of both scenarios. Only took perhaps 1 million years for random chemistry to stumble upon the specific molecular architecture that could store information while catalyzing its own replication. Only required the exploration of sequence space until chance encounters produced RNA molecules with both structural stability and catalytic function. Only needed the marriage of information storage with chemical catalysis to begin the transition from chemistry to biology. The irony rests in how the most sophisticated molecular system on early Earth arose through entirely random processes operating under the simple constraints of chemical thermodynamics. Ribozymes emerge as RNA molecules develop increasingly complex catalytic capabilities beyond simple self-replication. Some RNA sequences prove capable of catalyzing the formation of peptide bonds, creating the first examples of genetically encoded protein synthesis. Other ribozymes catalyze metabolic reactions that produce energy-rich molecules or modify other RNA sequences, beginning the development of the complex molecular networks that characterize living systems. Competition between different RNA replicators drives molecular evolution as sequences with superior replication rates outcompete those with slower reproduction cycles. This competition occurs entirely at the molecular level, with successful RNA sequences literally consuming the nucleotide building blocks needed by their competitors. The process creates evolutionary pressure for improved catalytic efficiency, higher replication fidelity, and resistance to degradation reactions. Cooperative interactions develop between different RNA molecules as some sequences prove capable of enhancing the replication of others through complementary catalytic activities. These early examples of molecular cooperation create the first primitive ecosystems composed entirely of competing and cooperating RNA replicators. The cooperative networks prove more stable and successful than individual replicators, establishing the principle that biological success depends on molecular teamwork rather than individual performance. Error correction mechanisms begin to emerge as RNA replicators develop sequences that can detect and repair replication errors in themselves and other RNA molecules. These proofreading functions operate through base pairing specificity that allows correct sequences to be distinguished from incorrect ones. The development of error correction represents a crucial step toward achieving the replication fidelity necessary for maintaining complex genetic information. RNA world ecosystems develop distinct niches based on different catalytic capabilities and resource requirements. Some RNA replicators specialize in rapid reproduction using abundant nucleotide resources, while others develop more complex catalytic functions that allow them to utilize scarce or chemically difficult resources. This ecological specialization creates the first examples of biological diversity based on functional rather than purely chemical differences. Template-directed synthesis becomes increasingly sophisticated as RNA molecules develop improved abilities to direct the synthesis of complementary sequences. The specificity of base pairing allows RNA templates to direct the assembly of their complements with much higher accuracy than random polymerization processes. This template-directed synthesis forms the foundation for all subsequent genetic replication systems. Molecular parasites emerge as some RNA sequences develop the ability to utilize the replication machinery of other RNA molecules without providing any reciprocal benefit. These parasitic replicators represent the first examples of purely selfish genetic elements that exploit the cooperative systems developed by their hosts. The presence of molecular parasites creates additional evolutionary pressure for the development of defensive mechanisms and more sophisticated replication control systems. Information storage capacity increases as successful RNA replicators develop longer and more complex sequences that can encode multiple catalytic functions within a single molecule. This increase in sequence complexity allows individual RNA molecules to perform multiple steps in metabolic pathways or replication processes, reducing their dependence on other molecules and improving their competitive success. The emergence of genetic codes begins as certain RNA sequences develop consistent associations between specific sequence motifs and particular catalytic functions. These protogenetic codes represent the first examples of the symbolic relationship between nucleotide sequence and molecular function that will later become universal among all living organisms. The codes develop through evolutionary processes that favor clarity and efficiency in the relationship between genetic information and molecular phenotype. Mutation rates in early RNA replicators balance the need for genetic stability against the requirement for evolutionary innovation. Too high a mutation rate destroys genetic information faster than selection can preserve beneficial changes, while too low a rate prevents adaptation to changing environmental conditions. The optimal mutation rate emerges through evolutionary processes that favor replicators capable of both maintaining their basic functions and adapting to new opportunities. Environmental selection pressures shape the evolution of RNA world ecosystems as different hydrothermal environments favor different types of molecular solutions to survival challenges. Temperature gradients, chemical compositions, and physical conditions vary between different vent systems, creating diverse ecological niches where different RNA strategies prove successful. This environmental diversity drives the rapid evolution of molecular complexity and functional specialization. Lipid membranes embrace the first organized chemistry as fatty acid molecules spontaneously form protective spheres around collections of organic compounds in the warm early seas. These amphiphilic molecules, possessing both water-loving and water-repelling regions, assemble into closed bilayer structures through purely physical processes that require no biological guidance or complex molecular machinery. The formation occurs spontaneously when fatty acid concentrations exceed critical micelle concentrations in the presence of appropriate salt levels and temperature conditions. Membrane formation follows thermodynamic principles that favor the creation of enclosed spaces where hydrophobic molecular tails cluster together while hydrophilic head groups interact with the surrounding water. This self-assembly process creates the first physical boundaries between organized chemical systems and the external environment, establishing the fundamental distinction between inside and outside that will characterize all future living cells. The lipid bilayers form closed vesicles that can encapsulate other molecules while selectively controlling what enters and exits their internal spaces. The chemistry of early membrane formation differs significantly from modern biological membranes in both molecular composition and physical properties. Early fatty acids contain irregular chain lengths and branching patterns that reflect their abiotic synthesis origins, creating membranes with unusual fluidity and permeability characteristics. These primitive membranes remain more permeable to small molecules than their biological successors, allowing easier exchange of materials between their interiors and the external environment. Vesicle stability depends critically on the chemical composition of the surrounding water, with changes in pH, salt concentration, or temperature dramatically affecting membrane integrity. The early oceans provide conditions that favor vesicle formation and stability, with appropriate ionic strength and temperature ranges that allow lipid bilayers to persist for extended periods. However, the chemical environment remains dynamic, creating selective pressure for membrane compositions that can tolerate changing conditions. Scientific research into early membrane formation relies heavily on laboratory experiments that attempt to replicate the conditions of the primitive oceans. These experiments demonstrate that simple fatty acids can form stable vesicles under conditions similar to those inferred for early Earth, but they also reveal the narrow range of chemical conditions required for membrane stability. The transition from laboratory demonstration to understanding how membranes could have formed and persisted in the chaotic environment of the early Earth remains challenging. The mystery of how early membranes became associated with replicating molecular systems represents one of the key questions in understanding the origin of cellular life. Membranes provide obvious advantages for protecting and concentrating molecular systems, but they also create barriers that can interfere with replication processes that require exchange of materials with the environment. Some researchers propose that early membranes were more permeable than modern cell membranes, allowing necessary molecular exchange while still providing organizational benefits. Only took a few 100,000 years for the random assembly of amphiphilic molecules to begin creating the enclosed spaces where complex chemistry could develop protection from environmental chaos. Only required the simple physics of hydrophobic interactions to establish the first boundaries between organized and unorganized matter. Only needed the spontaneous self-assembly of fatty acids to begin the long process of cellular evolution. The irony lies in how these simple physical processes created the foundation for the most complex organizational systems that would ever develop on Earth. Protocell formation occurs when vesicles successfully encapsulate collections of catalytically active molecules, creating enclosed systems where complex chemistry can proceed independently of external environmental fluctuations. These earliest protocells contain mixtures of organic molecules produced by hydrothermal synthesis, including amino acids, simple peptides, nucleotides, and primitive replicating systems. The encapsulation provides a controlled environment where molecular concentrations can build up to levels that support more sophisticated chemical interactions. Membrane permeability in early protocells allows selective exchange of small molecules while retaining larger molecular complexes within the vesicle interior. This selective permeability creates the first examples of chemical compartmentalization, where different reaction environments can be maintained in close proximity without direct mixing. The ability to maintain chemical gradients across membrane boundaries provides new opportunities for energy storage and controlled chemical reactions. Growth and division processes develop as successful protocells accumulate materials and energy that allow them to increase in size and eventually reproduce through membrane fission. The growth process follows physical principles that govern vesicle behavior, with membranes expanding as additional lipid molecules insert into the bilayer structure. Division occurs when growing vesicles become unstable and spontaneously split into smaller daughter vesicles that inherit portions of the original internal contents. Competitive advantages emerge among different protocell populations based on their membrane compositions, internal chemistry, and environmental adaptations. Protocells with more stable membranes persist longer in challenging chemical environments, while those with more permeable membranes may grow faster by accumulating resources more efficiently. This variation in protocell properties creates the first examples of selection operating at the level of organized cellular systems rather than individual molecules. Environmental factors strongly influence protocell survival and reproduction rates, creating selective pressures that drive the evolution of improved membrane systems. Temperature fluctuations test membrane stability, while chemical changes in the surrounding water challenge the ability of protocells to maintain their internal environments. pH changes can destabilize membranes or alter the chemistry of internal molecular systems, creating additional selection pressures for chemical robustness. Membrane composition evolution occurs as protocells with superior membrane properties outcompete those with less effective boundaries. Random variations in fatty acid composition create protocells with different membrane characteristics, and those with advantageous properties become more abundant through differential survival and reproduction. This evolution of membrane composition represents one of the earliest examples of adaptation at the cellular level. Internal organization develops within successful protocells as different types of molecules segregate into distinct regions based on their chemical properties and interactions. RNA molecules may concentrate in areas of the protocell where conditions favor their stability and function, while other organic compounds accumulate in regions where they can participate in metabolic reactions. This internal organization increases the efficiency of molecular interactions within the confined space of the protocell. Resource competition between protocells drives the development of more efficient mechanisms for acquiring and utilizing environmental resources. Protocells that can more effectively concentrate essential molecules from dilute environmental solutions gain competitive advantages over those with less efficient uptake mechanisms. This competition creates evolutionary pressure for the development of more sophisticated transport and metabolic systems. Symbiotic relationships begin to develop between different types of protocells, as some develop complementary capabilities that benefit both partners when they occur in close proximity. These early symbioses operate through chemical exchange between adjacent protocells, with waste products from one serving as essential nutrients for another. The symbiotic relationships represent the first examples of biological cooperation at the cellular level. Population dynamics of protocell communities follow ecological principles that govern competition, cooperation, and resource utilization in biological systems. Successful protocell lineages expand their populations when environmental conditions favor their particular adaptations, while less successful types decline in abundance. These population changes create feedback effects that influence the chemical environment and create new selective pressures for protocell evolution. The transition from simple vesicles to true cellular systems occurs gradually as protocells develop increasingly sophisticated internal organization and environmental interactions. This transition represents the emergence of biology from chemistry, as organized cellular systems begin to exhibit the properties of growth, reproduction, metabolism, and adaptation that characterize living organisms. The boundary between chemistry and biology becomes increasingly difficult to define as protocells develop more complex organizational properties. Metabolism's gentle dawn arrives as chemical pathways begin cycling energy through early cellular structures, transforming the random chemistry of the primitive oceans into organized networks of molecular transformation. These first metabolic systems operate without the complex enzyme machinery of modern cells, relying instead on the catalytic properties of mineral surfaces and simple organic molecules to drive the chemical reactions that sustain early life. Energy flows through these primitive systems like water, finding its course through an unmarked landscape, following thermodynamic gradients that favor the formation of energy-rich molecular bonds. The earliest metabolic pathways emerged from the chemical networks already operating in hydrothermal environments, where mineral-catalyzed reactions naturally produce the organic compounds needed for cellular chemistry. Iron-sulfur clusters serve as primitive catalysts for carbon fixation reactions that convert carbon dioxide into organic compounds using hydrogen gas as an energy source. These reactions operate efficiently under the reducing conditions of the early Earth, providing a sustainable source of organic carbon for growing cellular systems. Phosphorylation reactions begin to store chemical energy in high-energy phosphate bonds that can be broken to drive other metabolic processes. The early oceans contain abundant dissolved phosphate from the weathering of apatite minerals, providing the raw materials for phosphate-based energy storage systems. Simple organic phosphates form spontaneously under hydrothermal conditions, creating primitive versions of the energy-storing molecules that will later become universal among all living organisms. Fermentation pathways develop as cellular systems learn to extract energy from organic compounds through reactions that do not require external electron acceptors. These anaerobic processes break down simple organic molecules like glucose and amino acids, releasing energy while producing organic acids, alcohols, and other fermentation products. The fermentation reactions proceed rapidly under the warm conditions of the early oceans, providing cellular systems with reliable energy sources independent of external chemical gradients. The mystery of how complex metabolic networks emerged from simple chemical reactions remains one of the central challenges in understanding early life. Modern metabolism involves hundreds of interconnected chemical reactions organized into coherent pathways that maintain cellular energy balance and biosynthetic capacity. The transition from random chemistry to organized metabolism required the development of regulatory mechanisms that could coordinate multiple chemical reactions and maintain stable, steady-state conditions within cellular systems. Scientific investigation of early metabolism relies on comparative biochemistry studies that identify the most ancient metabolic pathways shared among diverse groups of modern organisms. These studies suggest that certain core metabolic reactions, particularly those involved in carbon fixation and energy storage, represent very ancient biochemical innovations that arose early in the evolution of cellular life. However, the specific sequence of metabolic evolution and the environmental conditions that drove its development remain subjects of active research. Only took a few 100,000 years for random chemical networks to begin organizing themselves into coherent metabolic systems capable of sustaining cellular growth and reproduction. Only required the gradual optimization of chemical reaction networks through evolutionary processes that favored more efficient energy utilization and biosynthetic capacity. Only needed the patient exploration of biochemical possibility space to discover the molecular mechanisms that could sustain life in the challenging environment of the early Earth. The irony lies in how these organized biochemical systems arose from the apparent chaos of early geochemistry. ATP synthesis emerges as cellular systems develop the ability to capture energy from environmental gradients and store it in the phosphate bonds of adenosine triphosphate. This universal energy currency allows cells to couple energy-releasing reactions with energy-requiring biosynthetic processes, creating the thermodynamic flexibility necessary for complex metabolism. Early ATP synthesis likely operated through substrate-level phosphorylation reactions that directly transfer phosphate groups from high-energy organic compounds to ADP molecules. Electron transport systems develop as cellular chemistry learns to extract energy from the movement of electrons between different chemical compounds. These early electron transport chains operate through simple organic molecules and metal ions that can exist in multiple oxidation states, allowing them to serve as electron carriers in redox reactions. The electron transport systems provide more efficient energy extraction from environmental chemical gradients than simple fermentation reactions. Biosynthetic pathways emerge as cellular systems develop the ability to synthesize the complex organic molecules needed for growth and reproduction from simpler environmental precursors. Amino acid biosynthesis allows cells to produce the building blocks for proteins, while nucleotide biosynthesis provides the materials needed for RNA replication and repair. These biosynthetic capabilities reduce cellular dependence on environmental sources of complex organic molecules. Metabolic regulation begins to develop as cellular systems evolve mechanisms to control the rates of metabolic reactions in response to changing environmental conditions and internal cellular states. Simple feedback inhibition systems prevent the overproduction of essential molecules, while allosteric regulation allows key metabolic enzymes to respond to cellular energy levels and metabolite concentrations. These regulatory mechanisms create the metabolic homeostasis necessary for stable cellular function. Carbon fixation pathways develop as cellular systems learn to incorporate inorganic carbon dioxide into organic compounds, providing a sustainable source of carbon for biosynthetic processes. The earliest carbon fixation reactions likely operated through reductive pathways that use hydrogen gas or organic compounds as electron donors to reduce carbon dioxide to organic carbon. These reactions operate efficiently under the reducing conditions of early hydrothermal environments. Energy coupling mechanisms emerge as cellular systems develop the ability to link energy-releasing reactions with energy-requiring processes through shared intermediates and common cofactors. This coupling allows cells to drive thermodynamically unfavorable reactions by pairing them with strongly favorable reactions, expanding the range of chemical transformations that cellular metabolism can accomplish. The energy coupling creates metabolic networks where energy flows efficiently between different chemical pathways. Cofactor systems develop as cellular metabolism begins to utilize small organic molecules and metal ions to facilitate enzymatic reactions. These cofactors serve as electron carriers, chemical activating groups, and catalytic centers that enhance the efficiency and specificity of metabolic reactions. The early cofactor systems likely included simple organic molecules like flavins and pterins that could be synthesized abiotically under hydrothermal conditions. Metabolic compartmentalization begins as cellular systems develop mechanisms to segregate different metabolic pathways into distinct cellular regions or organelles. This compartmentalization allows incompatible chemical reactions to occur simultaneously within the same cell and creates opportunities for establishing chemical gradients that can be used to drive energy-requiring processes. Early compartmentalization likely involves simple physical separation rather than complex membrane-bound organelles. Waste management systems emerge as cellular metabolism produces toxic or harmful byproducts that must be eliminated or neutralized to maintain cellular viability. These early detoxification systems likely involve simple chemical modifications that convert harmful compounds into less toxic forms that can be safely excreted from the cell. The development of effective waste management becomes increasingly important as metabolic complexity increases and produces a wider variety of potentially harmful byproducts. Autotrophy develops as some cellular systems evolve the ability to grow using only inorganic carbon sources, becoming independent of external sources of organic carbon compounds. This metabolic innovation allows cells to colonize environments where organic carbon is scarce while providing the foundation for primary productivity that can support more complex ecological systems. Early autotrophic metabolism likely operated through chemosynthetic pathways that extract energy from inorganic chemical reactions. The Archean Ocean's stillness stretches across 3 billion years of geological time, a vast liquid meditation where microbial mats spread like living carpets across shallow seafloors bathed in iron-rich waters. These earliest ecosystems exist in a world of perpetual twilight, where the sun shines through an atmosphere devoid of oxygen and thick with methane, creating skies that glow amber rather than blue. The ocean itself resembles no body of water that will ever exist again, tinted green with dissolved iron and warmed by the planet's residual heat to temperatures that approach those of modern hot springs. Stromatolites begin their slow construction as cyanobacterial mats trap and bind sediment particles, creating layered rock structures that will become some of the most ancient fossils preserved on Earth. These microbial reefs grow grain by grain, season by season, as countless generations of bacteria live, die, and become entombed within the calcium carbonate precipitates they help to form. The stromatolites rise like underwater cities built by microscopic architects, creating the first large-scale biological structures in Earth's history. Iron formations accumulate on the ocean floors as dissolved ferrous iron reacts with the earliest oxygen produced by photosynthetic bacteria, creating alternating bands of iron oxides and silica-rich sediments that record the planet's slowly changing atmospheric chemistry. These banded iron formations stretch for thousands of kilometers across the ocean basins, representing the largest mineral deposits ever created by biological processes. The iron bands preserve within their crystalline structure a record of seasonal cycles and long-term environmental changes that operated in the Archean seas. Microbial diversity flourishes in the chemical gradients that characterize different zones of the early ocean environment. Methanogens thrive in the deep, oxygen-free waters where they produce methane from carbon dioxide and hydrogen gas, while sulfate-reducing bacteria colonize sediment layers where they extract energy from sulfur compounds. Thermophilic bacteria occupy the hottest environments around hydrothermal vents, where they utilize chemical energy sources unavailable to other forms of life. The mystery of how these early microbial ecosystems maintain stability over such vast periods of time continues to challenge our understanding of ecological dynamics. Modern ecosystems undergo constant change and succession, rarely maintaining stable configurations for more than a few thousand years. Yet the Archean microbial systems apparently persisted with little fundamental change for hundreds of millions of years, suggesting that early life operated under different ecological principles than those observed in modern environments. Scientific reconstruction of Archean ocean chemistry relies on geochemical analysis of ancient sedimentary rocks that preserve chemical signatures of the early marine environment. Isotope ratios of carbon, sulfur, and other elements provide clues about biological processes operating in the ancient seas, while trace element concentrations reveal information about ocean temperature, pH, and dissolved oxygen levels. However, the extreme age of these rocks and their complex geological histories make interpretation of their chemical signals challenging and sometimes controversial. Only took 1 billion years for these simple microbial systems to explore most of the basic biochemical strategies that will ever be discovered by life on Earth. Only required the patient refinement of metabolic pathways and ecological relationships to create stable biological systems capable of persisting across geological timescales. Only needed the slow accumulation of biological innovations to begin the transformation of planetary surface chemistry. The irony rests in how these microscopically simple organisms accomplished feats of global environmental engineering that dwarf anything achieved by more complex life forms. Photosynthetic evolution begins as some bacterial lineages develop the ability to capture solar energy and convert it into chemical energy through increasingly sophisticated light harvesting systems. Early photosynthesis operates through simple photochemical reactions that extract electrons from hydrogen sulfide and other reduced compounds, avoiding the production of oxygen that would be toxic to most Archean life forms. These anoxygenic photosynthetic systems provide sustainable energy sources that allow biological productivity to expand beyond the chemical energy available from geological processes. Biogeochemical cycles develop as microbial metabolism begins to drive the circulation of essential elements between different environmental reservoirs, carbon cycles between atmospheric carbon dioxide, dissolved organic compounds, and biological tissues through the metabolic activities of diverse microbial communities, sulfur cycles between sulfate in seawater, hydrogen sulfide in sediments, and organic sulfur compounds in living cells through the activities of sulfur-metabolizing bacteria. Ecological zonation emerges as different microbial communities adapt to specific environmental conditions and establish stable population distributions across the diverse chemical gradients of the Archean Ocean environment. Photosynthetic communities dominate the shallow, sunlit zones where solar energy is available, while chemosynthetic communities colonize deeper waters where chemical energy sources remain abundant. Anaerobic communities thrive in oxygen-free sediments, while other bacterial groups exploit the intermediate chemical conditions found at the boundaries between different water masses. Chemical communication systems develop as microbial communities evolve mechanisms for coordinating their metabolic activities and responding to environmental changes. Quorum sensing allows bacterial populations to monitor their own density and adjust their metabolism accordingly, while chemical signaling between different species enables cooperative metabolic interactions. These early communication systems represent the first examples of organized biological cooperation beyond the cellular level. Symbiotic relationships emerge as different microbial species develop mutually beneficial associations that enhance their survival and metabolic efficiency. Syntrophic partnerships allow bacterial species to share the products of their metabolism, creating cooperative networks where the waste products of one species serve as essential nutrients for another. These early symbioses provide models for the more complex endosymbiotic relationships that will later give rise to eukaryotic cells. Seasonal cycles in the Archean Ocean create temporal patterns in microbial productivity and community composition that reflect changes in solar radiation, temperature, and chemical conditions. Photosynthetic communities exhibit seasonal blooms during periods of optimal light and temperature conditions, while chemosynthetic communities show different seasonal patterns related to changes in chemical energy availability. These temporal patterns create rhythmic fluctuations in ocean chemistry that become recorded in the geological record. Horizontal gene transfer operates extensively among Archean microbial communities, allowing rapid sharing of metabolic innovations and adaptive capabilities between different bacterial lineages. This lateral exchange of genetic information accelerates the rate of biochemical evolution and allows beneficial mutations to spread rapidly through diverse microbial populations. The extensive gene transfer creates highly interconnected evolutionary networks rather than simple branching phylogenetic trees. Mineral precipitation processes become increasingly influenced by biological activity as microbial metabolism affects the chemical conditions that control mineral solubility and crystal formation. Bacterial surfaces serve as nucleation sites for mineral precipitation, while metabolic processes alter local pH and chemical conditions in ways that promote or inhibit mineral formation. These biologically influenced mineralization processes create distinctive mineral textures and compositions that provide evidence for ancient biological activity. Population dynamics in Archean microbial communities follow ecological principles that balance competition for limited resources with cooperative interactions that enhance community stability. Boom and bust cycles characterize communities that depend on variable environmental resources, while more stable communities develop in environments where resource availability remains constant. These population dynamics create complex feedbacks between biological activity and environmental chemistry. Evolutionary innovations continue to accumulate as Archean microbial communities explore new metabolic strategies and environmental adaptations. The development of new enzyme systems allows exploitation of previously unavailable chemical energy sources, while improvements in cellular repair mechanisms enhance survival under harsh environmental conditions. These innovations gradually expand the range of environments that can support biological activity. Environmental engineering by Archean microbial communities begins to alter global ocean chemistry and atmospheric composition in ways that create new environmental conditions and evolutionary opportunities. Biological carbon fixation removes carbon dioxide from the atmosphere, while biological sulfur cycling affects the availability of sulfate and hydrogen sulfide in marine environments. These biological modifications of environmental chemistry represent the first examples of life actively reshaping planetary surface conditions. Cyanobacteria's quiet revolution begins in the shallow margins of the Archean seas, where blue-green bacterial mats develop the biochemical machinery to extract electrons directly from water molecules during photosynthesis. This metabolic innovation proves far more consequential than any previous biological development, as it harnesses the abundant hydrogen in seawater while simultaneously producing molecular oxygen as a waste product. The process operates with deceptive simplicity. Solar energy splits water molecules, liberating electrons for carbon fixation while releasing oxygen atoms that combine to form the gas that will eventually transform every aspect of planetary chemistry. The photosystem architecture that enables oxygenic photosynthesis represents one of the most complex biochemical innovations in the history of life, requiring the coordinated evolution of multiple protein complexes, electron transport chains, and energy transfer mechanisms. Photosystem 2 captures solar photons and uses their energy to extract electrons from water molecules, while Photosystem 1 uses additional photon energy to boost those electrons to energy levels sufficient for carbon dioxide reduction. The coupling of these two photosystems creates an electron transport chain that generates both ATP and reducing power while producing oxygen as an inevitable byproduct. Chlorophyll evolution provides the molecular foundation for efficient light harvesting as cyanobacteria develop increasingly sophisticated pigment systems that can capture solar energy across broader wavelength ranges. The chlorophyll molecules function as molecular antennae that funnel captured photon energy toward reaction centers where the actual photochemical reactions occur. These pigment systems evolve through gradual modifications of simpler light-harvesting molecules, with each evolutionary step providing incremental improvements in photosynthetic efficiency and environmental adaptation. The initial oxygen production occurs at extremely low rates, with individual cyanobacterial cells releasing only minute quantities of oxygen into their immediate surroundings. However, the cumulative effect of billions of photosynthetic cells operating continuously across millions of square kilometers of ocean surface begins to create measurable changes in local water chemistry. Dissolved oxygen concentrations start to rise in the shallow waters where cyanobacterial mats flourish, creating the first oxygenated microenvironments in Earth's history. Iron precipitation accelerates dramatically as dissolved ferrous iron in the early oceans encounters the oxygen produced by cyanobacteria, forming iron oxides that settle to the ocean floor as rust-colored sediments. This reaction removes both iron and oxygen from the water column, preventing the immediate accumulation of free oxygen while creating the distinctive banded iron formations that characterize late Archean and early Proterozoic sedimentary rocks. The iron precipitation serves as a chemical buffer that delays the atmospheric accumulation of oxygen for hundreds of millions of years. The mystery of how cyanobacteria survived their own toxic oxygen production remains one of the fascinating puzzles of early evolution. Oxygen damages cellular components through oxidative stress reactions that break down proteins, lipids, and nucleic acids. Yet cyanobacteria somehow evolved protective mechanisms that allowed them to tolerate the oxidizing conditions they created. Some researchers propose that early cyanobacteria evolved sophisticated antioxidant systems, while others suggest that oxygen production was initially so low that cellular damage remained manageable. Scientific understanding of early cyanobacterial evolution relies heavily on molecular phylogenetic studies that trace the evolutionary relationships among modern cyanobacterial lineages. These studies suggest that oxygenic photosynthesis evolved only once in Earth's history, in a common ancestor of all modern cyanobacteria, and that this innovation occurred sometime between 3.5 and 2.8 billion years ago. However, the fossil record of early cyanobacteria remains sparse, making precise dating of this crucial evolutionary transition difficult. Only took a few 100 million years for this single biochemical innovation to begin reshaping the entire planetary environment. Only required the evolution of molecular machinery capable of splitting water molecules to initiate the most dramatic environmental transformation in Earth's history. Only needed the patient accumulation of oxygen production across countless generations of photosynthetic bacteria to begin the oxidation of an entire planet. The irony lies in how this life-sustaining process initially operated as a form of planetary poisoning that threatened the very organisms responsible for its production. Ecological succession in cyanobacterial communities follows patterns determined by oxygen tolerance and competitive ability under increasingly oxidizing conditions. Early cyanobacterial species likely possessed limited oxygen tolerance and thrived only in environments where oxygen concentrations remained low due to rapid consumption by iron oxidation reactions. As oxygen production increased and iron availability decreased, new cyanobacterial lineages evolved with enhanced oxygen tolerance and competitive advantages under more oxidizing conditions. Geographic expansion of cyanobacterial populations occurs as successful photosynthetic lineages colonize new marine environments and establish populations in previously uninhabitable locations. The ability to generate their own energy from sunlight allows cyanobacteria to survive in nutrient-poor environments where chemosynthetic organisms cannot maintain viable populations. This competitive advantage drives the rapid spread of cyanobacterial communities across the global ocean system. Cellular innovations develop as cyanobacteria evolve increasingly sophisticated mechanisms for managing the challenges of oxygenic photosynthesis. Specialized cellular compartments concentrate photosynthetic machinery while isolating oxygen-sensitive cellular components from oxidative damage. Protective pigments screen out harmful ultraviolet radiation that could damage photosynthetic systems, while repair mechanisms fix damage to cellular components caused by oxidative stress. Metabolic flexibility emerges as some cyanobacterial lineages develop the ability to switch between oxygenic and anoxygenic photosynthesis depending on environmental conditions. This metabolic versatility allows these organisms to survive in environments where oxygen accumulation would otherwise inhibit their growth, while also providing backup energy systems during periods when oxygenic photosynthesis becomes difficult or impossible. Symbiotic relationships begin to develop between cyanobacteria and other microbial organisms as the oxygen production creates new ecological niches for organisms capable of utilizing oxygen in their metabolism. Aerobic bacteria evolve respiratory pathways that use oxygen as an electron acceptor, allowing them to extract more energy from organic compounds than anaerobic fermentation processes. These aerobic organisms often form close associations with cyanobacteria, creating early examples of oxygen-based ecological partnerships. Carbon isotope signatures in sedimentary rocks begin to reflect the massive scale of biological carbon fixation occurring through cyanobacterial photosynthesis. The preferential incorporation of light carbon isotopes into organic matter creates distinctive isotopic patterns that can be detected in ancient rocks, providing geochemical evidence for large-scale photosynthetic activity. These isotopic signatures allow scientists to track the expansion of cyanobacterial populations across geological time. Seasonal cycles become more pronounced as cyanobacterial productivity responds to changes in solar radiation, temperature, and nutrient availability. Photosynthetic blooms during optimal growing seasons create pulses of oxygen production that affect local and regional ocean chemistry, while winter die-offs reduce oxygen production and allow anaerobic conditions to return. These seasonal patterns create cyclical fluctuations in ocean chemistry that influence the evolution of other marine organisms. Environmental feedback mechanisms develop as increasing oxygen production begins to affect global atmospheric and oceanic chemistry in ways that influence cyanobacterial growth and survival. Rising oxygen levels create more oxidizing conditions that favor certain cyanobacterial lineages while inhibiting others. While changes in atmospheric composition affect solar radiation patterns and ocean chemistry, these feedback loops create complex interactions between biological activity and environmental conditions. Genetic innovations accumulate as cyanobacterial populations explore new evolutionary strategies for improving photosynthetic efficiency and environmental adaptation. Gene duplication events create opportunities for the evolution of new photosynthetic proteins, while horizontal gene transfer allows beneficial mutations to spread rapidly through diverse cyanobacterial communities. These genetic mechanisms accelerate the rate of evolutionary adaptation to changing environmental conditions. Chemical warfare strategies emerge as different microbial communities compete for space and resources in increasingly crowded marine environments. Some cyanobacteria begin producing toxic compounds that inhibit the growth of competing organisms, while other microbial groups develop resistance mechanisms or countertoxins. These biochemical conflicts create additional selective pressures that drive the evolution of chemical defense and offense systems. Multicellular organization begins to appear in some cyanobacterial lineages as individual cells develop mechanisms for adhering to each other and coordinating their metabolic activities. These early multicellular forms create more complex three-dimensional structures that can exploit environmental gradients more effectively than individual cells. The multicellular organization also provides protection against environmental stresses and predation by other microorganisms. Global impact assessment reveals that cyanobacterial oxygen production represents the most significant biological modification of planetary environment in Earth's history, comparable in scale to major geological processes like volcanism and tectonism. The cumulative effect of cyanobacterial photosynthesis over hundreds of millions of years fundamentally alters atmospheric composition, ocean chemistry, and the availability of chemical energy for biological processes, creating the oxidizing environment that will support all future complex life. Iron bands mark ancient seasons across the ocean floors as dissolved metals precipitate in rhythmic layers that record the planet's slow transition from a reducing to an oxidizing world. These banded iron formations stretch like geological sheet music across thousands of kilometers of sea floor. Their alternating layers of red iron oxides and dark silica creating visual rhythms that preserve the chemical pulse of early Earth. Each band represents a delicate balance between oxygen production by photosynthetic bacteria and iron dissolution from volcanic activity, creating chemical precipitation cycles that operate on timescales ranging from seasonal to millennial. The precipitation process follows chemical principles that govern iron oxidation in aqueous solutions. As ferrous iron dissolved in the early oceans encounters oxygen produced by cyanobacteria and spontaneously converts to ferric iron oxides. Hematite and magnetite crystals form through nucleation and growth processes that concentrate iron into dense mineral phases that settle rapidly through the water column. The precipitation removes both dissolved iron and free oxygen from seawater, creating a chemical sink that prevents oxygen accumulation while generating the largest iron ore deposits in Earth's history. Seasonal variations in the banded iron formations reflect annual cycles in biological productivity, ocean circulation, and volcanic activity that control the rates of iron supply and oxygen production. Thick iron-rich bands form during periods of high volcanic activity when iron input to the oceans exceeds oxygen production capacity, while thin silica-rich bands develop during periods when reduced iron supply allows oxygen to accumulate and suppress further iron precipitation. These seasonal signals preserve detailed records of early Earth's environmental variability. Chemical gradients develop in the water column as iron oxidation reactions create distinct zones with different redox chemistry and mineral precipitation behavior. Surface waters, where photosynthetic bacteria concentrate, become progressively more oxidizing, while deeper waters maintain reducing conditions where dissolved iron remains stable. The boundary between oxidizing and reducing water masses migrates vertically in response to changes in biological productivity and ocean mixing, creating complex three-dimensional patterns of chemical precipitation. The mystery of how banded iron formations maintain their extraordinary lateral continuity across entire ocean basins remains one of the puzzling aspects of early marine chemistry. Modern chemical precipitation processes typically create localized mineral deposits with limited geographic extent. Yet banded iron formations extend for thousands of kilometers with remarkably consistent chemical and physical properties. Some researchers propose that early ocean chemistry was more uniform than modern seas, while others suggest that specialized circulation patterns distributed precipitating materials across vast distances. Scientific analysis of banded iron formations provides detailed insights into early ocean chemistry through examination of their mineral compositions, trace element contents, and isotopic signatures. Iron isotope ratios preserve information about the biological processes that controlled iron cycling, while rare earth element patterns reveal details about seawater chemistry and hydrothermal activity. However, the complex post-depositional changes that affect these ancient rocks can obscure their original chemical signatures and complicate environmental interpretations. Only took about 1 billion years for these chemical precipitation processes to remove most of the dissolved iron from the world's oceans, while simultaneously consuming enormous quantities of biologically produced oxygen. Only required the patient operation of oxidation chemistry to begin transforming ocean composition from iron-rich to iron-poor conditions. Only needed the gradual accumulation of iron oxide layers to create geological formations that preserve detailed records of early environmental change. The irony rests in how these chemical processes that created some of Earth's most valuable mineral resources operated as a temporary buffer that delayed the oxygenation of the entire planetary atmosphere. Trace element chemistry in the iron formations reveals information about the diverse sources of metals that contributed to early ocean composition. Nickel, chromium, and platinum group elements derived from meteorite impacts create distinctive chemical signatures in some iron formation layers, while volcanic contributions add vanadium, titanium, and other lithophile elements. Hydrothermal inputs contribute copper, zinc, and sulfur compounds that create additional chemical complexity in the precipitating iron minerals. Crystal growth mechanisms in the iron formations follow kinetic pathways that depend on temperature, pH, and the availability of nucleation sites in the precipitating solutions. Rapid precipitation creates fine-grained iron minerals with high surface areas and reactive properties, while slower precipitation allows larger crystals to form with more stable mineral structures. The crystal size and morphology patterns preserve information about the environmental conditions under which precipitation occurred. Diagenetic processes modify the iron formations after burial as elevated temperatures and pressures drive recrystallization reactions that alter mineral compositions and textures. These post-depositional changes can enhance iron ore quality by concentrating iron into higher-grade mineral assemblages, but they also destroy some of the original environmental information preserved in the freshly precipitated sediments. Understanding these diagenetic modifications is crucial for interpreting the environmental significance of ancient iron formations. Biological influences on iron precipitation extend beyond simple oxygen production to include direct microbial involvement in iron oxidation and mineral formation processes. Some bacteria accelerate iron oxidation through enzymatic pathways that utilize iron as an electron acceptor, while others influence mineral precipitation through the production of organic compounds that serve as nucleation sites or crystal growth modifiers. These biological effects create mineral textures and compositions that differ from purely inorganic precipitation. Geographic distribution patterns of banded iron formations reveal information about early ocean basin geometry and circulation patterns that controlled the transport and mixing of iron-rich and oxygen-rich water masses. The largest iron formations occur in areas that experienced active hydrothermal input of dissolved iron, while smaller deposits formed in more distal locations where iron concentrations were lower. These distribution patterns help constrain models of early ocean chemistry and circulation. Temporal evolution of iron formation chemistry shows progressive changes in mineral composition and trace element patterns that reflect the long-term evolution of ocean chemistry and atmospheric composition. Early iron formations contain mineral assemblages that indicate highly reducing conditions, while later deposits show evidence for increasingly oxidizing environments. These temporal trends document the gradual transition from the iron-rich Archean oceans to the oxygenated Proterozoic seas. Economic significance of banded iron formations extends far beyond their scientific value, as they constitute the source of most of the world's iron ore resources and support much of global steel production. The high iron content and favorable mineral compositions of these ancient deposits make them essential raw materials for modern industrial civilization. The irony lies in how these products of early Earth's reducing atmosphere now fuel an industrial society dependent on oxidizing combustion processes. Correlation between different iron formation sequences allows reconstruction of global environmental changes and the synchronization of early Earth history across different continents and ocean basins. Similar chemical patterns and timing relationships between iron formations from different parts of the world provide evidence for globally coherent environmental changes rather than localized chemical anomalies. These correlations support models of early Earth as an integrated planetary system. Environmental implications of iron formation deposition include massive changes in ocean chemistry, atmospheric composition, and the availability of chemical energy for biological processes. The removal of dissolved iron eliminated one of the major electron acceptors available for early metabolism, while the consumption of oxygen delayed atmospheric oxygenation and maintained reducing conditions favorable for anaerobic life. These chemical changes influenced the evolution of early life and set the stage for the eventual oxygenation of Earth's surface environment. Experimental studies of iron formation processes use laboratory simulations to investigate the chemical kinetics and environmental conditions required for iron precipitation under early Earth conditions. These experiments reveal the critical roles of pH temperature, dissolved oxygen concentrations, and biological activity in controlling iron mineral formation. However, the complexity of natural systems and the long timescales of geological processes make it difficult to fully replicate iron formation conditions in laboratory settings. The Great Oxygenation begins its inexorable transformation of Earth's surface chemistry as dissolved oxygen finally starts accumulating in seawater after hundreds of millions of years of consumption by iron oxidation reactions. The transition occurs not as a sudden event, but as a gradual tipping point, where oxygen production by cyanobacteria finally exceeds the chemical oxygen demand of dissolved metals and reduced compounds in the early oceans. Free oxygen molecules begin to persist in solution for the first time, creating chemical conditions that will prove both toxic to existing life forms and essential for the evolution of more complex organisms. Atmospheric leakage marks the critical threshold where oceanic oxygen concentrations reach saturation levels and oxygen gas begins escaping from seawater into the overlying atmosphere. This outgassing process fundamentally alters atmospheric composition as molecular oxygen displaces methane, hydrogen, and other reducing gases that have dominated Earth's early atmosphere. The atmospheric oxygen concentrations rise slowly, reaching perhaps 1% of modern levels during the initial phases of oxygenation, but even these low concentrations prove sufficient to trigger massive changes in atmospheric and surface chemistry. Chemical cascades develop as atmospheric oxygen begins driving oxidation reactions throughout the surface environment, converting reduced minerals to oxidized forms and altering the chemical availability of essential elements. Sulfur chemistry undergoes particularly dramatic changes as hydrogen sulfide gas becomes oxidized to sulfur dioxide and sulfate, fundamentally changing the pathways through which sulfur cycles between atmospheric, oceanic, and biological reservoirs. These chemical cascades create positive feedback loops that accelerate the oxygenation process once it begins. Mass extinction events eliminate many of the anaerobic organisms that dominated Earth's early biosphere, as rising oxygen concentrations create toxic conditions for life forms that evolved under reducing environments. Methanogenic bacteria suffer particularly severe population crashes as atmospheric oxygen levels suppress methanogenesis, while simultaneously oxidizing the methane that previously provided these organisms with energy and carbon sources. The extinction represents one of the most severe biological crises in Earth's history, eliminating perhaps 99% of existing species. The mystery of how some anaerobic organisms survived the oxygenation crisis and persist to the present day remains one of the fascinating aspects of early evolutionary history. These surviving lineages apparently found refuge in environments that remained oxygen-free, such as deep sediments, anaerobic water bodies, and the intestinal tracts of other organisms. Their persistence demonstrates that complete sterilization of anaerobic environments never occurred, allowing ancient metabolic strategies to survive alongside newer aerobic innovations. Scientific reconstruction of the Great Oxygenation Event relies on multiple lines of geological and geochemical evidence that preserve signatures of changing atmospheric and oceanic chemistry. Paleosol compositions record the oxidation of surface minerals, while sedimentary sulfur isotope ratios preserve information about atmospheric sulfur chemistry. Red bed formations document the widespread oxidation of iron-bearing minerals in terrestrial environments, providing additional evidence for rising atmospheric oxygen levels. Only took about 300 million years for this chemical revolution to completely restructure Earth's surface environment and create the oxidizing conditions that persist to the present day. Only required the crossing of a critical threshold where biological oxygen production exceeded chemical oxygen consumption to initiate irreversible changes in planetary chemistry. Only needed the patient accumulation of photosynthetic organisms to overcome the chemical inertia of a reduced planet. The irony lies in how this life-supporting transformation initially operated as an environmental catastrophe that eliminated most existing life forms. Adaptive radiation follows the extinction crisis as surviving organisms evolve new metabolic strategies that can exploit the opportunities created by oxygenated environments. Aerobic respiration develops as some bacterial lineages learn to use oxygen as an electron acceptor, allowing them to extract far more energy from organic compounds than anaerobic fermentation processes. These aerobic organisms gain enormous competitive advantages in oxygenated environments, driving rapid evolutionary diversification and ecological expansion. Redox chemistry throughout the surface environment shifts towards more oxidizing conditions as atmospheric oxygen creates new pathways for electron transfer reactions and mineral weathering processes. Iron minerals convert from reduced forms like pyrite and siderite to oxidized forms like hematite and goethite. changing the color of sedimentary rocks from dark greens and grays to the reds and yellows characteristic of oxidized iron. These redox changes affect the availability of trace metals and other elements essential for biological processes. Ozone layer formation begins as atmospheric oxygen undergoes photochemical reactions in the upper atmosphere that produce ozone molecules capable of absorbing harmful ultraviolet radiation. This protective ozone shield reduces the intensity of UV radiation reaching Earth's surface, creating safer conditions for surface-dwelling organisms while also affecting atmospheric chemistry through ozone's role as a powerful oxidizing agent. The ozone layer represents one of the first examples of life creating environmental conditions that benefit itself. Biogeochemical cycles undergo fundamental reorganization as the presence of atmospheric oxygen creates new pathways for the circulation of carbon, nitrogen, sulfur, and other essential elements between atmospheric, oceanic, and biological reservoirs. Carbon cycling becomes dominated by the oxidation of organic matter through aerobic respiration, while nitrogen cycling develops new oxidation and reduction pathways that will later become essential for biological nitrogen fixation. Continental weathering accelerates dramatically as atmospheric oxygen drives the oxidation of sulfide minerals and organic matter in exposed rocks, increasing the rate at which chemical weathering processes break down continental crust and deliver dissolved ions to the oceans. This enhanced weathering affects ocean chemistry by increasing the availability of nutrients like phosphorus and nitrogen, while also affecting pH through the production of organic and inorganic acids. Evolutionary innovation accelerates as the new chemical environment created by oxygenation provides opportunities for the development of metabolic pathways and cellular structures impossible under reducing conditions. Aerobic metabolism allows much more efficient energy extraction from organic compounds, while the oxidizing environment enables the formation of disulfide bonds that stabilize protein structures and allow more complex molecular architectures. Ecological reorganization creates entirely new types of biological communities as aerobic and anaerobic organisms establish spatial and temporal patterns of coexistence that allow both metabolic strategies to persist in the same environments. Stratified communities develop where aerobic organisms occupy oxygenated surface waters, while anaerobic organisms persist in oxygen-free deeper waters or sediments. These ecological patterns create complex biogeochemical gradients that influence nutrient cycling and energy flow. Mineral precipitation patterns change dramatically as rising oxygen levels alter the solubility and transport properties of many metal ions, leading to the formation of new types of sedimentary deposits and the cessation of others. Ion formation deposition ends as dissolved iron becomes oxidized and precipitated before reaching the open ocean, while new types of oxidized mineral deposits begin forming in continental environments. These mineralogical changes create distinctive geological markers of the oxygenation event. Global climate effects develop as atmospheric oxygenation affects radiative balance through changes in atmospheric composition and surface albedo. The replacement of methane by oxygen eliminates a powerful greenhouse gas while simultaneously creating more efficient pathways for organic carbon oxidation. These climate effects may have contributed to the Paleoproterozoic glaciation events that occurred during the later stages of atmospheric oxygenation. Long-term consequences of the Great Oxygenation Event extend far beyond the immediate chemical and biological changes, establishing the oxidizing surface environment that will persist for the remainder of Earth's history and creating the chemical foundation for all subsequent evolution of complex life. The event represents a permanent transition in planetary evolution, demonstrating how biological processes can fundamentally alter planetary chemistry and create irreversible changes in environmental conditions. Complex cells find their way through the oxygenated seas as endosymbiosis creates the cellular architecture that will support all future multicellular life. The process begins when larger bacterial cells engulf smaller ones without digesting them, creating internal partnerships where the engulfed bacteria continue living and reproducing within their hosts. These endosymbiotic relationships prove mutually beneficial as the host cells provide protection and nutrients, while the endosymbionts contribute specialized metabolic capabilities that enhance their host's survival in the newly oxygenated environment. Mitochondrial evolution occurs as aerobic bacteria become permanent residents within larger anaerobic cells, bringing with them the sophisticated respiratory machinery needed to extract energy from oxygen while protecting their hosts from oxidative damage. The endosymbiotic bacteria retain their own DNA and reproductive systems while gradually transferring many of their genes to the host cell nucleus, creating an integrated cellular system where nuclear and mitochondrial genomes work together to maintain cellular function. This partnership allows the combined cell to thrive in oxygenated environments that would be toxic to either partner alone. Chloroplast acquisition happens later as some eukaryotic cells engulf cyanobacteria and convert them into photosynthetic organelles, creating the first photosynthetic eukaryotes and establishing the foundation for all plant life. The cyanobacterial endosymbionts bring with them the complete photosynthetic apparatus developed during billions of years of bacterial evolution, including the sophisticated light harvesting systems and carbon fixation pathways that make oxygenic photosynthesis possible. The host cells gain the ability to synthesize their own organic compounds from atmospheric carbon dioxide, while the endosymbionts receive protection and nutrients. Nuclear organization develops as eukaryotic cells evolve increasingly sophisticated mechanisms for organizing their genetic material within membrane-bound nuclei that separate DNA replication and transcription from the cytoplasmic environment where protein synthesis occurs. This compartmentalization allows more complex regulation of gene expression and protein production, while protecting the genetic material from the oxidative damage that becomes more common in oxygenated environments. Nuclear membranes also provide opportunities for controlling molecular transport between different cellular compartments. The mystery of how endosymbiotic relationships became established and maintained over evolutionary time remains one of the fascinating questions in cell biology. Modern cells rarely engulf other living cells without killing them, making it difficult to understand how the initial endosymbiotic partnerships could have formed and persisted long enough to evolve into permanent organelles. Some researchers propose that early eukaryotic cells had less effective digestive systems that allowed engulfed bacteria to survive, while others suggest that environmental stresses favored cellular cooperation over competition. Scientific evidence for endosymbiotic origins of organelles comes from multiple lines of molecular and cellular research that demonstrate the bacterial ancestry of mitochondria and chloroplasts. DNA sequence analysis shows that organella genomes are most closely related to specific groups of bacteria, while ultrastructural studies reveal that organelles retain many characteristics of their bacterial ancestors, including double membrane systems and ribosomes similar to those found in bacteria rather than eukaryotic cells. Only took perhaps 200 million years for these cellular partnerships to evolve from temporary associations into permanent organella systems that revolutionized cellular metabolism and energy production. Only required the gradual integration of endosymbiotic bacteria into host cell biology to create the complex cellular architecture that characterizes all eukaryotic life. Only needed the patient evolution of molecular mechanisms for coordinating the activities of multiple genomes within single cells. The irony lies in how this fundamental cellular innovation arose through the merger of separate organisms rather than through the evolution of new cellular machinery. Cytoskeletal development provides eukaryotic cells with sophisticated internal scaffolding systems that allow precise control of cellular shape, internal organization, and movement capabilities. Actin filaments, microtubules, and intermediate filaments create dynamic networks that can rapidly reorganize in response to cellular needs, enabling complex cellular behaviors like directed movement, internal transport, and precise chromosome segregation during cell division. These cytoskeletal systems require energy from ATP hydrolysis and sophisticated regulatory mechanisms to coordinate their activities. Endomembrane systems evolve as eukaryotic cells develop increasingly complex networks of internal membranes that compartmentalize different cellular functions and allow specialized organelles to develop distinct chemical environments. The endoplasmic reticulum provides sites for protein synthesis and modification, while the Golgi apparatus processes and packages proteins for transport to specific cellular destinations. These membrane systems enable much more sophisticated cellular organization than possible in bacterial cells. Sexual reproduction emerges as eukaryotic cells develop mechanisms for combining genetic material from two different individuals, creating offspring with novel genetic combinations that enhance evolutionary adaptability. The evolution of sexual reproduction requires complex cellular machinery for chromosome pairing, genetic recombination, and the production of specialized reproductive cells. But it provides enormous evolutionary advantages by increasing genetic diversity and accelerating adaptive evolution. Multicellular organization begins as some eukaryotic cells develop mechanisms for adhering to each other and coordinating their activities to create organized tissue structures. These early multicellular organisms start as simple cellular aggregates, but gradually evolve more sophisticated mechanisms for cellular communication, differentiation, and specialized function. Multicellularity allows organisms to grow larger, occupy new ecological niches, and develop specialized tissues for different functions. Gene expression regulation becomes increasingly sophisticated as eukaryotic cells evolve complex mechanisms for controlling when and where different genes are activated, allowing single genomes to produce many different cell types with specialized functions. Transcriptional regulation, post-transcriptional processing, and epigenetic modifications provide multiple levels of control over gene expression, enabling the development of complex developmental programs and cellular differentiation pathways. Chromosomal organization evolves as eukaryotic cells develop mechanisms for packaging their much larger genomes into organized chromosome structures that can be accurately segregated during cell division. Histone proteins provide scaffolding for DNA organization, while specialized chromosome structures like centromeres and telomeres ensure proper chromosome function. These organizational innovations allow eukaryotic cells to maintain much larger and more complex genomes than bacterial cells. Metabolic integration occurs as the different compartments and organelles within eukaryotic cells develop coordinated metabolic pathways that efficiently utilize resources and energy while maintaining cellular homeostasis. Mitochondrial respiration provides ATP for energy-requiring processes throughout the cell, while other organelles contribute specialized metabolic functions like lipid synthesis, protein processing, and waste management. This metabolic coordination requires sophisticated regulatory mechanisms and transport systems. Evolutionary consequences of eukaryotic cell evolution extend far beyond changes in cellular organization, as the increased complexity and metabolic efficiency of eukaryotic cells creates opportunities for the evolution of large, complex multicellular organisms that will eventually dominate many terrestrial and marine environments. The cellular innovations that characterize eukaryotes establish the foundation for all subsequent evolution of plants, animals, and fungi. Environmental interactions change dramatically as eukaryotic cells develop new capabilities for sensing and responding to environmental conditions, moving through their environments and manipulating their surroundings in ways that bacterial cells cannot achieve. These enhanced environmental interactions create new ecological relationships and evolutionary pressures that drive further biological diversification and complexity. Symbiotic relationships continue to evolve as eukaryotic cells form new partnerships with bacterial and other microbial organisms, creating complex ecological networks where different organisms provide complementary functions that benefit all participants. These ongoing symbiotic relationships demonstrate that cellular cooperation remains an important evolutionary strategy even after the establishment of permanent organella systems. Ocean's eternal meditation settles into its long rhythm of tides and currents as the ancient seas carry life's potential toward distant shores and future possibilities that stretch beyond imagination into deep time. The water itself has become a living system, permeated with microscopic organisms that transform sunlight into chemical energy while exhaling the oxygen that will sustain all complex life to come. Waves lap against primitive shorelines where stromatolites rise like stone flowers, their layered structures preserving within calcium carbonate the patient work of countless bacterial generations that have learned to build homes from dissolved minerals and captured light. The ocean breathes now with a rhythm older than continents, its circulation patterns driven by temperature gradients, tidal forces, and the spinning of a planet that rotates more slowly than it did when water first began to fall. Deep currents carry nutrients from hydrothermal vents towards surface waters, where photosynthetic communities convert carbon dioxide into organic compounds, while surface currents transport oxygen-rich water toward the deeper realms, where it will sustain the respiration of organisms that have learned to extract energy from the marriage of organic carbon and atmospheric oxygen. Chemical gradients stretch through the water column like invisible landscapes, where different communities of microorganisms thrive in their preferred conditions of temperature, pressure, and dissolved chemistry. Near the surface, cyanobacteria and early eukaryotic cells harness solar radiation in the bright, warm waters where photosynthesis proceeds most efficiently. In the middle depths, communities of bacteria cycle nitrogen, sulfur, and carbon through complex metabolic networks that connect the productive surface waters with the nutrient-rich depths. At the bottom, near the sediment interface, anaerobic communities continue their ancient metabolisms in the oxygen-free environments that preserve the chemical conditions of Earth's earliest seas. Seasonal cycles now govern biological productivity as orbital mechanics create annual rhythms in solar radiation that drive periodic blooms of photosynthetic organisms followed by die-offs that rain organic matter toward the ocean floor. These cycles create temporal patterns in ocean chemistry that influence the evolution of biological rhythms and metabolic strategies, while also affecting global climate through changes in atmospheric gas concentrations and oceanic heat transport. The mystery of what lies ahead in deep time remains as profound as ever. As the ocean carries within its dissolved chemistry and living communities the seeds of evolutionary possibilities that will unfold across geological ages yet to come. The molecular innovations that have emerged during these first billions of years, photosynthesis, respiration, cellular organization, and metabolic complexity provide the foundation for biological experiments in form and function that will eventually populate every environment from deep ocean trenches to mountain peaks. Scientific understanding of these early developments provides glimpses into the patient processes that have shaped our planet's surface environment and created the conditions necessary for our own existence. The ocean serves as both archive and laboratory, preserving within its sediments the chemical signatures of early environmental changes while continuing to host the biological processes that maintain planetary habitability. Each drop contains dissolved minerals that have cycled between rock and water for billions of years, carrying information about ancient climates, extinct ecosystems, and the gradual accumulation of biological innovations. Only took 4 billion years for chemistry to discover biology, for random molecular interactions to organize themselves into self-replicating systems, and for those systems to evolve the complexity necessary to begin transforming planetary surface conditions. only required the patient operation of thermodynamic principles, evolutionary processes, and environmental feedbacks to create a living world from a sterile one. Only needed the inexorable flow of energy from nuclear fusion in the sun to drive the chemical reactions that built the molecular machinery of life. The irony rests in how this vast epic of planetary transformation, spanning geological ages and involving countless innovations and extinctions, created the stable environmental conditions that allow complex organisms like ourselves to exist for the briefest moments in cosmic time. The ocean continues its ancient work as tides rise and fall according to gravitational forces that connect Earth to the Moon and Sun, while currents transport heat, nutrients, and organisms across vast distances that link all marine environments into a single planetary system. Waves break against shores where the first tentative experiments in multicellular organization are beginning to explore the possibilities of colonial life, cellular differentiation, and coordinated tissue function. Dissolved gases maintain the delicate chemical balance that sustains both aerobic and anaerobic life. With oxygen concentrations high enough to support efficient respiratory metabolism, but low enough to allow anaerobic processes to continue in protected environments. Carbon dioxide levels regulate the acidity of seawater while providing the raw material for photosynthetic carbon fixation that forms the base of marine food webs. The temperature of these ancient seas remains warmer than modern oceans, heated by the planet's residual internal energy and the closer proximity of a moon whose gravitational influence drives more powerful tidal mixing. This warmth accelerates chemical and biological processes while creating thermal gradients that influence ocean circulation and the distribution of nutrients throughout the water column. Silence, profound, as the cosmic void settles over waters that have learned to sustain themselves through the patient circulation of matter and energy between living and non-living systems. The ocean sleeps now with the deep rest of geological time, its surface barely rippled by winds that blow across a world where continents remain small and scattered, where the atmosphere glows faintly with auroras driven by solar radiation interacting with the planet's magnetic field, where the night sky blazes with stars unfiltered by atmospheric pollution. In this stillness, the ocean dreams of futures yet to unfold, of complex cells that will learn to build shells and skeletons, of multicellular organisms that will discover movement and sensation, of ecosystems that will develop predation and symbiosis, of life forms that will eventually leave the water and colonize the land. But for now, the ancient seas rest in their mineral cradle, breathing slowly with the rhythm of tides, carrying within their vast volume the accumulated wisdom of 4 billion years of chemical and biological evolution. The water itself has become a memory palace where every molecule holds stories of its journeys through rock and air and living tissue, where every dissolved ion carries information about the weathering of mountains and the metabolism of microbes, where every current preserves the legacy of planetary processes that operate on timescales beyond the reach of individual consciousness. And in this eternal meditation, the ocean waits,